1, 2, testing. 1, 2.
Perfect. Okay, so
this
did
is
you,
done. Yeah.
sorry, you can finish talking.
Oh yeah, I was just saying maybe we need to be in the remote rooms anyways because we're running short of volunteers.
Yes, exactly. So that was my next point. So Oceanus 4, 3, and 6, right? These have no volunteers in the morning.
Yeah.
So I've asked, so between three of you, Bhakti, you, and you, do you want to monitor these ones?
Yeah.
Right,
I'll be in 6.
And
It's
so
not
then,
remote one.
do you want to be in 6?
Yeah.
So I asked Bhakti to be in 6. You can ask her to go to another one. I mean, I had asked her to be here and there. So.
Oh, okay. Yeah, that's fine. She'll be here.
Yeah.
She'll
No,
be
but if you have particular interest in staying at a workshop to watch a talk or something, then you might have to like ask the other person to cover the other room and stuff like that.
No,
So I'll leave that between you three.
Yeah.
Okay.
Okay.
Yeah, you can pick first. I'll pick the remainder.
And also this message below Katrina's
yeah.
thing of which rooms you will be covering.
Yeah.
So that Katrina knows that it is being looked at.
I haven't even like looked at the talk names.
Right.
I'll like.
Oh yeah, me neither. I've just given up on. So this is so now we have a personal incentive, right? You're like, oh, different talks don't get recorded. I won't be able to see the talk.
Yeah.
True.
Until next time I have to see that.
I've been getting all my work from talking with people right after they've presented.
Yeah.
They gave me like the TLDR version.
So
nice.
welcome to the hallway track prime time.
Yeah.
Yep.
So, I mean, I think most of them can carry on by themselves fine, except the remote ones. So, yeah, just now at 9.
Oh yeah, so what?
They're all live, right? Every single one is live?
No, there is room 3 that I still don't see live. I think at SPLASH'23 or
Room 3 is PLMW,
yeah,
that's what.
Morning.
Okay.
Okay.
The Edward dude.
Ah.
Yeah.
All the others seem to be live.
Yep. Okay. Well, did you fix the 23rd thing?
Let's see.
Oh yeah, that's exactly what
That
I
was
was.
actually on room 3.
That's exactly what I was fixing. Okay, fix it.
Okay.
And what is the other one that I had?
It was just room 3.
Room
Oh,
7.
room 2.
Wow.
Oh, a bunch of them. Yeah, room 7 and room 2.
This is the reason why you should do it at night.
Yeah, oh my god.
Did you finish that assignment?
I did. We submitted it, but we didn't finish our crash program, and we just submitted it, but let's say, yeah, the deadline to submit was midnight EST.
Wow.
So,
Morning.
morning.
Hey.
Yeah. So,
Are the choppers working?
Dr. Chair, they're all.
We have to find the student volunteers we talked to yesterday because they have outdated information.
What happened?
Are they video text?
Yes.
There is a video tech and AVR channel. It's called
Video.
I don't think
video
I am.
tech test.
Yeah.
I don't think I am in that channel.
I don't think they're in this channel because I looked at the people. I don't think they're in here.
Can you add to them?
I am
You
not
can,
in this
because
channel.
you don't know who they are.
Yeah, I don't remember their names. I don't know do you remember their names?
No idea. And I'm trying to find the emails on Discord. Not working so far. What about just a bit?
Oh, no, it's at 10:15. Okay, we can.
Yeah, so maybe like 30 to 45 minutes beforehand.
I
and
want
just find the
to
list.
stay in 6 the entire time. You can come at 10.
Okay.
Over the
J-O-A-O.
okay.
It's just.
No, that's the professor, that's it.
I didn't.
J to
We don't
JD.
do it. It just.
Yeah, this
Even if we have to do the bookmark, we could do it super fast.
It's so stupid that they cannot search for the nickname.
What I'm
Just
worried
for
about is
the username.
volunteers
of the
messing up with
So
it.
stupid.
That's what I don't want.
Yeah, why?
Mm,
So we have one.
So that's why I just want to sit there.
if you want to,
I know.
I can.
One.
I can just,
Who's this?
John Doe.
Yeah. I think the most common first and last names in the world is Mohammed Leah.
Okay, so I am going downstairs.
Or something.
Yeah.
Sometimes like,
I'm going downstairs.
Okay.
And
I'm gonna
because
say,
I want to check room 12 and also room 3. Check if Ashwala needs help.
okay.
Please come check in 3.
Yeah, Peter.
I want to work on the people, I guess I'm working.
So the main thing is start streaming so that I can go live here and before we
T und Rösch.
dois, um, dois, três, um, dois. Um, dois, três. Um, dois, três. Dois, três. Um, dois, três. Um, dois, três. Um, dois, três. Um, dois, três. Ah. Um, dois, três. Um, dois. dois, um, dois.
I'm going to find someone who will do the because so that I can check that everything.
Oh, to check the.
Hey, what's up? What's up, man? So the system's running. Yeah. Check this out. Seems like yesterday we just back to the keyboard and now yesterday. It's keyboard. So when you don't mess. Hi, I'm the video guy. That will be the I'm taking video, audio, video.
I'm manager shall be one of the support volunteers.
Yeah, thank you very much. Thanks for helping out. It's quite sophisticated this Discord and
Right, so you'll be handling the video.
Yeah.
And for anything else, I think you'll be helping out.
Yes, and I think there's another volunteer here because this is two workshops in here, right?
Yes, it's a joint workshop.
PDP and
That's a joint
Joint.
session.
yes.
But there are still talks.
Yeah, there's two
Yeah.
talks. We'll just have the participants of 2 meetings hopefully going on. Yeah.
I see. Okay. Oh, so BPDP was in Oceanus first,
Yes.
and you moved it here.
For
Yes.
this one meeting,
It's just one.
one session, it's a joint.
I see. Okay. Was that updated on the program?
Or should be no problem.
Or you wouldn't know because you're not BPDP, right? Because BPDP made the change.
Yes.
Right. Okay.
I already closed the
Right. Yeah. Makes sense.
chair.
I mean, it's just for attendees so that they know that not to go in that room and stuff.
No, but it's in the schedule to come here and the chair
For
the
PPDP,
session.
right?
Yes.
I was just confirming because this was a last minute change. So I need to come.
And hello, I'm Remy. I'm giving the presentation
Hi.
now, and I just wanted to come and check, say I'm coming, but I also had some problem with registration, so I'm doing that
Okay.
now. So I just go finish the registration and then I'll be back to
Sure.
set everything in like 5 minutes. Sorry, my name is Richard. All right. Yeah, hey, sorry, nice to meet you. Nice to meet you. Yeah, I'm in a bit of a panic. No, maybe we just take the time after that.
All right. So the camera is here.
I just wanted to be able to
Anybody here will. So you are the one.
Okay, so I just came back here and I'll be back in a minute. Thank you. Yes, my name is
Yeah, I'm not sure.
I'm the chair of so thank you very much for doing this.
Yes.
Hi, Sandra. Hi, Sandra. Yes, we had a lot of email. Thanks a lot. Yeah. Yes, thank you. It's very kind of you. So, the joint talk, yes.
That's fine. Coming back to as long as not long.
Many years ago,
Yeah.
2010,
So what do you
and Lobster 2020.
Yeah.
So it's really like two conferences that I really
Enjoy.
feel
Yeah.
part of.
Yeah. Yeah.
So I'm really like things.
Yeah.
However, I'm wondering whether my computer will.
Yes, our video.
Yeah, because it's an old one and
Yeah.
it doesn't
Santiago.
connect to
Right? Your first name is Santiago. Just
Yes,
it has to be.
yes. Yeah, many people is complaining that it's like the bigger thing is that they do the subject. Many people is complaining the bigger thing to be the subject.
say I got maybe okay.
The subject is the big people.
So you can just.
Because of the size is the scope.
Okay.
So maybe you don't know me,
We
but
don't have
Maybe when we met or
yes,
maybe
yes,
just
but I mean I know you very well
Thank you very much.
because I did a meeting with Maria Puente
No.
in Valencia in Basel evaluation.
Yeah.
I work with Spencer again from Illinois.
Yeah.
I cannot guarantee.
Jose and Maria do Basel evaluation for months.
Yeah.
Okay, so we publish the last year before she's retired.
No.
Yes.
Really?
Hello.
I can speak. Hello. Hmm? Yes. Hello? Okay.
So, hello, nice to meet you. So,
Hi.
I'm a volunteer for Lobster. So, my name is Kazuki Kemori.
Yes, you had a talk yesterday, right? At PPDP.
Ah, yes, 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 yes.
I'm Ana Jorge.
So
I'm a volunteer
Nice to
here.
meet you.
Nice
So
to meet
for
you too.
PPDP,
dois, um, dois, três.
Because I was a bit worried when I saw the registration number was 25. And I thought, you know, if 25 registered, 50 will come. Do you get questions from the virtual participants? Yes. And you as a chair, you speak in this microphone?
Yes.
Yeah.
Yeah. That's the thing that is, all the speakers are, I mean, not,
Flexible.
yeah, that you have to stay there.
Yeah. And you as a chair also use this microphone?
Well,
Or
what I did yesterday,
Like after the I don't see your signal for some reason.
oh, okay.
Oh yeah, that's good.
Yeah, I haven't put it.
It took me a little time yesterday to understand how it
Yes, you
works.
have to take it.
Yes, in Apollo,
Yes.
putting,
I was trying, the first time I was trying to
Yes, yes,
gently
everyone.
take it out, but it doesn't.
hi, so hi Roland. So I'm nice to meet you. So I'm a student volunteer for Lobster. So my name is Kazuki Kemori.
Then maybe your resume has shown.
Oh yeah, that's right. So yeah, so my advisor.
So Dr. has helped us a lot with this one.
Yeah, yeah. But so it's not good for you.
Let's see, I've just connected it.
You connected it just now.
Yeah.
So yes,
It
I
might
attended,
take a little bit, but
Yeah, it takes about 10 seconds.
Sorry, I just came yesterday. I missed your presentation.
Okay, so nice to meet you.
no.
So let me go to the restroom.
Yeah, yes, we are. So, I mean, we have virtual participants, and I think they need to write questions
Yes.
in Discord.
I think I can, we can together monitor.
Yeah.
Yes, I am monitoring
Yeah,
that.
okay,
Yes.
thank you. So if there's a virtual,
We
why you
monitor it.
yeah.
another.
Can I try?
Yeah, yeah, sure.
Maybe you can.
If you look, if
It
you,
comes here, right?
Ah,
What do you
okay.
want to do? You just want to present it, right?
Perfect. Yeah,
So
yeah,
it's just extension on the screen
yeah,
of the other
it's
side.
just an additional
So yeah,
one.
you have to. Okay, let me try to
Push,
see if I can
push.
make it full screen. View. Enter full screen. Okay,
Perfect.
and now maybe you can just do this. Okay. Sarah.
Yeah,
Cool.
it works.
Yeah.
Seems to work. Thank you so much.
So I removed the thing for now, but it's working, so don't worry.
Yeah, okay.
welcome.
So, yeah, welcome everybody, the participants here in the room and also our virtual participants to this first joint session of Lobstra and PPDP, featuring an invited talk by Maribel Fernandez from the King's College in the UK. This is also the first session of Lobstra, so a few words about Lobstra. Lobstra is the logic-based program synthesis and transformation meeting. It's held for the 33rd time, so this means it has been held for an amazing 30 years now. The meeting takes place today and tomorrow, and all 6 sessions will be in this room, 3 sessions today and 3 sessions tomorrow. The proceedings are now online, the Springer lecture notes proceedings, and you can find a link on our homepage. The invited presentation will be followed by a short presentation on certified proof checkers. This is the first short presentation of Lobstra. I think that's basically all I wanted to say. So welcome again, and I declare Lobstra officially opened, and I pass the baton on to Escobar Santiago.
Well, so I'm the chair of PPDP, so there are some people from PPDP okay, that came. Oh, yes, it's true. No, well, but in PPDP, it's very loud. Well, in PPDP, we have been doing this thing, okay? So we take the microphone, okay? People in Lobster, you will get used, okay? So remember that you have to speak to the microphone all the time. So it's my, sorry for the joke. So welcome, okay? So people of Lobster, so PPDP and Lobster have been together for many years, okay? So it's a very nice common community, okay? So welcome people in Lobster, okay? And those of PPDP that came here, okay? So you can stay for the rest of the session, okay? And then we will have more stuff, okay, after lunch, okay? And, well, it is my pleasure, okay, to have Maribel Fernandez here as invited speaker, okay? So she's an expert in so many things, okay? And I met her many years ago. I'm so happy to have her here, okay? But I think that this topic, okay, that is not showing, but that we will...
Is it possible to switch?
No, but it's okay, yeah, but this topic is a very interesting one, okay? Binding operators in general, okay, and not the nominal effort that she has been doing for years, okay? And I think that it is a very important effort, okay, and a very interesting talk. So, thank you, whenever you want.
Thank you, Santiago, for the introduction, and I'd like to start by thanking the chairs and the program committees for both conferences, which are conferences I really feel part of these communities. I've been attending them for many years, and so I'm really very happy to be here giving this talk, and also in this very beautiful place. And I want to also give a special thanks to ALP, which is the Association for Logic Programming, and they are sponsoring my talk here. So like Santiago was saying, this is, we are discussing in this talk an approach to specification of problems, specification of systems, where some of the operators in the system are what we call binders. And what I'm going to describe in this talk is part of an effort from a lot of people, so it's like a teamwork. My collaborators for this particular topic that I'm going to discuss today in nominal techniques come from different areas in the world. So some are in Brasilia, like Daniele and Gabriel and Ana Rocha, and some in Washington, some in the UK. Some are my PhD students, and also Andy Pitts and Jamie Gabay, who were the proposers of the nominal approach for binding. So without all of them, I wouldn't be able to tell you these things now. So let me just briefly give you an overview of what we would like to discuss today, to cover today. So first of all, the idea of languages with binders. I think this is something that everybody is aware, but there are different ways of seeing it, so just we will agree on what we call a system with binder, a language with binder. Then I would like to introduce nominal logic, which is the basis for the approach we use, and then discuss the main topic, really, of this talk, which is how do we work with these expressions that have binders, and in particular, how can we check equivalences, and then more than that, solve, for example, equations between terms that might have these binders. So the popular notion of unification, which is at the center of logic programming, but also very useful in the area of functional programming. Although we use matching rather than unification to compute, we still want to use unification to analyze properties of functional languages. And in particular, within rewriting systems, if you define your functions with rewrite rules, unification is the key concept, for example, to compute critical pairs, to understand overlaps in definitions. So we will talk about unification. And also, in particular, unification in systems which arise often when we are doing equational reasoning. We often have operators that have some properties. So we work modulo axioms. We say modulo, for example, modulo commutativity, modulo associativity and commutativity. So typically, processes in the pi calculus or in other concurrent systems, they are defined using operators like parallel composition, which have these additional properties like associativity and commutativity. So we also want to look at how these things combine, the notion of binder and the notion of an equational theory. Okay, so these are the main papers that I've used to prepare this talk. You see that they range over many years. Andy Pitts introduced nominal logic in 2003, and we had a paper just this year looking at nominal AC matching. So it's a long-term effort. Let me give first a couple of examples, just as I say, to set the context so that we know what we are talking about. When I say a binder, what I mean is the kind of thing that you find, for example, in languages like the ML family that have a let, or Haskell that have a let. Okay, let is a binder. In the lambda calculus, which I guess is the most familiar system for many people, the lambda is a binder. I mentioned before the pi calculus. The pi calculus also has a binder called nu. And this probably is the most basic, is the one that I usually, when I give this kind of talk, and there are students, undergraduate students in particular, that's my favorite one, because it's the one that everybody has seen. For all existential, we know they are binders in first-order logic. Okay, but what does it really mean that they are binders? Because this is kind of usually presented in an informal way. So you might introduce first-order logic to your first-year students and just tell them, pay attention, for all an existential is a binder. It means you can rename the variable. But as I say, that's kind of an intuitive way of saying it. And here we would like to be able to formally define this notion of binder, so that then we can also reason with these systems. We can prove properties. So the intuitive notion, as I said, is that you rename. However, it's a bit tricky because you need to rename avoiding capture, etc. So if you want to really define it formally, I say it's quite tricky, and it's, for example, many of the definitions, even original well-known papers like Church's definition for the lambda calculus had some problems in the definition of the alpha equivalence relation. It's a tricky relation to define, this relation of changing names. So we can implement it in a first-order system, in any programming language, basically. If you need to do this in C or in any programming language, you can implement this renaming as an encoding in your syntax. You encode your expressions, and you hard code these renamings. You might decide, for example, to represent your variables with indices. So instead of for all x greater than 0, it will look something a bit odd with these indices, but it can be done. And if you do that, if you move down to the really plain encoding, things are okay, they work well. You can do easily comparisons. For example, you can compare if two expressions are the same quite easily because you use the same, supposedly the same indices. So it's matching and unification is easy and efficient, but you pay a price, which is, well, first the effort, because encodings are usually heavy, and second, it's not so easy to then understand what you've got. Okay, when you see an encoded expression, it's not really so easy to understand it. And if you want this to reason with the system, it's not great. And also, okay, the last point, there are no meta variables in your encoding. No, so it works well if you have the full expression, you encode it. But what if you have an expression where some parts you don't really know yet? Maybe this is, I don't know, a process, an expression in the bicalculus where you have defined some part of it, but your collaborator is working on another part of that process expression. And so what you have is one part is defined, the other part is a big X. Okay, something will come there. So that makes these encodings very tricky. And that's what I mean by no meta variables. There is a much more elegant, more abstract approach, which uses, is what is usually called the higher order approach. So what you do there is that you choose a meta language that already has a formal notion of a binder. Okay, so for example, what we call higher order rewriting systems, which are various versions. For example, CLOP introduced combinatory reduction systems, and in the meta language, there is the lambda calculus. Okay, so you assume already, you know what a binder is, lambda, you know the properties of that lambda calculus, and then you can define things, other things, using that. So clearly, it's very easy to define the lambda calculus in that system because it's already part of your infrastructure. But you can also define, obviously, if you want to define other things like processes, or you want to define first-order logic formulas, and then you want to define a rule to simplify them or to put them in pre-next normal form, or to do that sort of thing. So that's quite easy compared with the version where you have to encode everything. So there are, say, various approaches, various frameworks that follow this approach of representing systems with binders using a formalism that already has binders in them. So it's elegant, it's easier to work with it, perhaps, but you need to be a bit careful because if your framework is quite powerful, for example, if it already has the lambda calculus in it, then if you are interested, for example, on checking for equivalences or unifying your expressions, you are doing it modulo those things you have in the framework, and unification modulo beta is not decidable, okay? So you need to restrict yourself to fragments where things work well, which there are fragments, like, for example, the one defined by Dale Miller. So what we propose here with the nominal approach is a different, if you want something more in the middle, okay? What we really want is alpha, the alpha equivalence relation. That's what binding means. We don't want beta. We don't want to have to encode everything. So we want something in the middle that covers just alpha. And the key idea that Gabay and Pitts proposed is to, rather than move to the theory of functions with the lambda calculus, is to stay in set theory, plain set theory, except they chose a particular set theory, which was called nominal set theory, which includes the notion of a name. Okay? In sets, you can have names. And with names comes this interesting concept of swapping. You can swap names. So their names, their nominal sets are sets with names and with a permutation action on the names defined by these swappings. So based on that, it's possible to define a notion of abstraction. So to define equivalence classes that represent the alpha equivalence relation. So let me tell you a little bit more concretely. Nominal logic is a theory in first order logic that uses these concepts I was just telling you. So let's assume we have names and we have a possibility of swapping names. What does it mean? It means that I have some variables in my logic that I consider them to be names or name sorts. It's a sorted logic. So I have variables of sort name. The A's and A primes there have sort name. And these axioms tell me how this swapping works. Okay? So we axiomatize swapping. So the swapping can act on names. It can act on terms, like I can swap A and A prime on a term f of x, or on a predicate, or I can define this abstraction syntax. For the moment, it's just syntax with the brackets. If I move from here, I'm not going to be in the microphone. Okay, here, those brackets. So for the moment, just syntax, but we will also have axioms to define what those brackets are in a minute. So here, those F axioms are, you don't need to read all these. I'm just is to give you the idea that this is a formal theory in first order logic that axiomatizes the notion of swapping names, the notion of a name being fresh for a term. So the F axioms tell you when a name is fresh in a term, fresh meaning it's not free there. And then, what else you've got? These axioms. They are the ones that define these square brackets that I told you is just syntax. It's only syntax. This is first order logic. But because of these axioms, we can understand these brackets as abstractions. So the first one, for example, tells you when two abstractions are equal. Basically, they are equal either because they have the same abstracted name and they are equal, okay, identical, or if they have different abstracted names, it's because if you swap the names, you get the same thing, okay? So it's a way of defining the notion of alpha in a formal way, just using first order logic. And based on that, we can then define languages with binders. So we have the syntax I just mentioned, first order terms, where if I want something to be a binder, I will use the abstraction with the brackets. Obviously, the substitution I have there is just a first order substitution. The variables are first order variables, so it's not a fancy notion of substitution. It's just replacing, it's like grafting, except that, you can do swappings, permute names. But this is fortunate that because this way of formalizing the binder only addresses the alpha relation, there's nothing else there. There's no beta, there's no extra things. We can, so Pitts and Gabay and Urban showed that unification is decidable. Not only that, it's also unitary. So like first order unification, like the one in Prologue, you have one most general solution when things are unifiable. So concretely the syntax we use. So what we are going to use in the rest of the presentation is where we want to talk about variables. These are like the first order variables, okay? We use capital letters. When we want to talk about names, we call them sometimes atoms, we use little letters, lowercase letters. Function symbols are like in first order logic. We use them to build expressions. And we use these square brackets for abstraction. It's always abstraction of a name and a term. And we allow ourselves to suspend permutations on variables, okay? So if you come from the higher order abstract syntax world, you would probably call those meta variables, not variables. Or if you are just don't care about this and you work on the lambda calculus, when you write, lambda xm to define the beta rule, for example, lambda xm, the x is the name you want to abstract with the lambda, and the m represents the body of the abstraction. It's a meta variable, you could say, or in our case, it is a variable, okay? We don't have meta variables, we just have variables, like in first order logic, and some of them are names, and we put them with little lowercase letters. And the idea is that permutations can suspend on the variables. Why? Because the variables represent parts of the expression that you don't know yet. So if there is a swapping that you're trying to do, some permutation of names you're trying to do, that needs to wait until you know what that x is. Okay? That's why the permutation suspends on x. So pi is simply a permutation, really changing names. Okay? Bijection, finite bijection on names. It could be empty, of course. When it's empty, we don't write it. We just put x. And you can use this syntax to represent, for example, the syntax of ML using just terms. So these are abstract syntax trees, you see. There's nothing more in them, just trees. So if you want to represent an abstraction, lambda a t, when you write lam, that's your root, and then abstract a t. Okay? So it's really the syntax that you would put in Prolog. Okay? It's just first order syntax. But, so you can define, for example, the let rec in ML, which binds the f, the function, the recursive function you're defining, and the argument a. And of course, you can sugar that, so you can use the normal syntax, but it corresponds to the abstract syntax you have there, to the trees you have there. And then we have, on that plain syntax, we have, like I mentioned before, there's an axiomatization of the alpha equivalence relation, which is straightforward. If you forget the one about the variables, okay? So if you have a ground term, a ground expression, let's say a lambda term, okay? It's not lambda xm, it's lambda xx or lambda xy or whatever. So you can check the equality of those two expressions by using these rules here. The tricky one is when there are parts you don't know in your expressions. In that case, you can only say that those things are equal if the suspended permutations that you might have on these unknown expressions do not affect x, which is what this ds pi prime means. The different set of the permutations, the places where the permutations give different results, cannot appear in x. Okay, so that's the only, perhaps, non-standard rule you have to come up with if you want to axiomatize alpha here. So, for example, using this, we can derive the formula there. We know that ABX is equal to x, provided that A and B are fresh in x. Or you can know that lambda AX is equal to lambda B, ABX, provided that B is fresh in x. So there is one more thing that I should have highlighted, which is the rules for abstraction. Okay, the rules for abstractions are these axioms I explained before that say AS is equal to IT because they have the same abstracted name. It's just sufficient that S and T are equal. But if you have two different names, A and B, you will need to check that S is equal to the result of swapping A and B in T. So basically, you translate them both to an abstraction in A. But it's important that A is fresh in T, because if T has the name A free, these two things will never be equal, since S has abstracted A, okay? So that's why we have this condition A fresh for T, and that means we need to also axiomatize the freshness conditions, which corresponds to the axioms in nominal logic I showed you before. This just is an inductive definition of when something is fresh. So note, for example, that A is fresh in the abstraction of A in S. Again, the only rule that might be slightly, I think if I asked you all to do it, you would do this directly. Perhaps the only one that needs a little bit of thinking is the one for the variable. When is A fresh in pi x? Well, I need to check pi minus 1 of A. That needs to be fresh for x. So we can derive, again, freshness things that we need for these things using those rules. So you see that we derive alpha equivalences under assumptions of freshness for variables. Okay? We can derive lambda ax equal to lambda b abx under the assumption that b is fresh for x. So freshness assumptions are important in this system. And so with these notions we have now, we can, for example, define term transformations, rewriting. So nominal rewriting is rewriting with these expressions. You can define equational theories, you can do algebraic specifications, define operational semantics of programs or processes. And this is an example where we use nominal rewriting to define the prenext normal form of a first-order logic formula. So these rules work on the expressions I just defined, where the brackets are defining abstractions. It means that the rewriting relation is working modulo the alpha equivalence relation. So the first rule, for example, can apply to some expression P. This is using infix notation, okay? The conjunction and appears in fix. But if you look at the top rule, P and an expression of the form for all, which has an argument, which is an abstraction, okay? So I will be able to rewrite using this rule, even if I have for all B something, okay? Because the matching will be done modulo alpha. And as you can see, these are just plain rewriting rules. They rewrite trees. Okay, I take a tree and I rewrite it. The only thing different from what a first-order rewrite language or Prolog would do is that it's modulo alpha. You can define the lambda calculus if you want, because in this system it's not part of the meta language. So if you're interested in the lambda calculus, you need to define it. And to define the lambda calculus, you will need to define the substitution of a name for a term. And then there, you see that in higher order rewriting systems, for example, the beta rule is just one rule because it profits from the framework having already substitution defined in it. But our first order systems, nominal systems, the substitution they have is the first order one, so it's not enough to implement the lambda calculus. So we add this. So you can see this as a kind of explicit substitution version of the lambda calculus, except that the explicit substitution rules are just rewrite rules that take advantage of the fact that we have a system that can work modulo alpha. So we don't need to encode with indices or that sort of thing, okay? Yes?
Normally, this is the place where you need to define alpha conversion. And there is none. I mean, normally you need to check that the Y is not an abstraction when you do the substitution.
Okay, so the place where you check that there is no capture is when you move the substitution under a lambda. So that's the sigma lambda rule there, okay? This one. This one moves the substitution for A under the lambda. And it has a condition. Okay, so it moves the substitution. Yeah, okay. So it moves the substitution provided that B is fresh for Y, so it's not going to be captured. Okay, so that's where you see it doesn't do capture.
But what if it isn't?
Well, it doesn't really matter because, so I need to go back to the axioms and perhaps emphasize that we are in, with this nominal set semantics, with the axiomatization we have, the names don't have any particular meaning in themselves. So all names are represented just by a name. That's why we call them sometimes atoms, because they don't have structure. And these axioms, which sometimes are called equivariant axioms, tell you, in particular, look at the one on P. So if a predicate holds for X, you have the right to swap names in X, and it needs to work too. So you cannot, predicates are equivariant. The nominal relation is equivariant, which means that when we generate rewrite steps, I should have emphasized this better. When we generate rewrite steps, so because this is done modulo alpha, we can use any variant of this rule for any names. So if I put this sigma lambda in my system with A and B don't have any privileges in my system, okay? They are just two atoms. So if this works for A and B, it works for C and A. So if you happen to rewrite a term that has B inside Y, just take the variant of the rule that uses C, right? So that's why it makes it so easy to define, for example, the explicit substitution for the lambda calculus, because you don't need to, in a system like using the brand, you would need to have the shifts and lifts and all that, but here you don't. So that is the part that is in the framework, okay? Just the alpha part. So the interesting thing is that because we kind of keep quite low down in the abstraction hierarchy, we are kind of first order plus these permutations. There are efficient algorithms. So I don't know if you recall this, but for first order terms, like in Prolog, for example, the unification algorithm is linear. There are two very efficient ones, one by Martelli Montanari, one that uses graph by Peterson and Wegman. So those very efficient algorithms can be also used to check equivalence and unify terms modulo alpha. So in that sense, we are in a little bit better situation than if we had moved really far with a higher order framework, which makes things easy. So in a higher order framework, you wouldn't have needed the sigma rules for the lambda calculus. But the price to pay is that you then have to be careful when you're manipulating your expressions. So how do you build an algorithm for checking alpha equivalence or making unification? You just turn the rules I gave you into simplification rules. So this is the idea of Martelli Montanari's unification algorithm. I don't know if you recall that from at some point studying the unification algorithm for Prolog, maybe. Martelli and Montanari work with multi-sets of expressions, multi-sets of equations. So we do the same thing here. We work with multi-sets of problems, and then apply simplification rules depending on the shape of our equation. So some of these simplification rules just eliminate equations, others decompose equations, etc. The interesting ones are the ones at the bottom that tell you if you have two abstractions with different names, that's where the decomposition needs to do a swapping and check for the freshness. Okay. So, and obviously you need also the rules to simplify freshness, because you generate freshness. For example, the rule for abstraction with A and B generates A fresh for L. So your algorithm then needs to simplify the A fresh for L using the simplification rules there. So this is to check equivalence. If you want to unify, you need also instantiation rules. Okay, but this is enough for checking equivalence. So you might want something more than checking equivalence. You might want to find a substitution that makes two terms equal. In this context, it will be a substitution with a freshness context, okay? Or you might simply want to match things. When you match, you only instantiate the variables in one of the terms. The other one is supposed to be ground, or you consider you don't care if it has variables, you can't instantiate those. So matching is what you use in functional programming or to generate a rewriting relation. Unification is what you would use in a logic programming language. So these are just a couple of examples. So if you want to unify lambda AX with lambda BB, because we are unifying modulo alpha, the solution the algorithm would give you is that you need to instantiate X with A, and you don't need any freshness context, okay? But if you wanted to unify lambda AX with lambda BX, then the algorithm would tell you that you don't need a substitution, it's the identity, but you do need some freshness assumptions, okay? So these are the solutions that the simplification algorithm would give you. So nominal matching is decidable. You have one most general solution, and that's really good, because if we are going to use matching to generate a rewriting relation, it's good that we have that. Regarding complexity, so it's almost as good as in the ground case. It's actually as good as in the ground case, in the first order case, if you have ground expressions. So suppose you have terms in the lambda calculus or terms in a process calculus, and you want to check equivalences, just modulo alpha. So if your expressions are both ground, the checks have the same complexity as first order unification or matching or check. But if you are working with, for example, matching a term where you want to instantiate the variables on the left-hand side with a term that has itself variables, but you need to consider them like frozen variables, okay? That increases the complexity, it's log linear. And finally, if you really want the case where you have non-ground, non-linear expressions, it can go up to quadratic complexity. That's for matching or just alpha equivalence check. When you do unification, things become more complicated, and we couldn't define an algorithm that is linear, okay? So for matching and alpha equivalence, we can mimic the first order complexity. But for unification, the first order unification algorithm is linear, and we couldn't get that. However, there is a linear unification algorithm for Miller's patterns, higher order patterns, which correspond to nominal terms. So the question was, why is there this linear algorithm for higher order patterns and ours is quadratic? But I think the issue is you measure with respect to the syntax, to the size of the input, and the inputs in the nominal case are quite compact. You see, they are like first order terms. So if you have an X, you just have X, whereas in the higher order pattern, you would have X applied to A1, A2, A3, AN. So the syntax, the correspondence between the syntax of an expression in nominal terms and the equivalent in a pattern has an explosion in size, okay? So maybe that is what explains why the pattern unification is linear on the size of the input, but we couldn't get it better than quadratic. However, if you translate our problem into the pattern problem, our size n can become sine n squared, okay? But it's a conjecture, and we haven't yet found the proof for this. So it's still an open problem. So we have algorithms for this. We have formalizations both in Coq and PBS that have been done by students in Brasilia. Okay, So this is what I was telling you before, that the rules are defined modulo permutative renamings. This is what people call equivariance. This I already mentioned. So nominal matching is what I was describing before. That's matching modulo alpha. That is the one I was talking about with the complexity. Now, if you want the equivariant problem, so if you are not just checking if two expressions are matchable with a freshness context and substitution, but you also want to know whether there is a variant of the expression modulo permutations that can match, that's the equivariant matching problem. It's also decidable. However, that is exponential. Okay? But luckily, it's not a problem that comes up normally. So we proved that what we call closed nominal rules, the ones that don't have free atoms appearing in the expressions, in the terms, if you have closed nominal rules, then alpha is sufficient to get you all the variants. You don't need to also try to make variants by using permutations. So with closed nominal rules, nominal matching is sufficient, and that's the one that has the really good complexity. We also proved that closed rules are sufficient to encode higher order rewriting systems. Higher order rewriting systems normally impose also this way of writing your terms that doesn't allow to have free names. You can have free variables, but not free names. So all the examples I gave you before are closed, therefore you can do nominal matching in an efficient way, which is why there are some languages that already have been defined using this, and there are packages for, in particular, the one for Isabel developed by Christian Urban is quite popular. It was used, so the nominal package in Isabel was used by Larry Paulson to formalize Gödel's theorems, and he says in his paper that he really used extensively the properties of nominal terms. So, but what happens then with rewriting-based languages? So this is what triggered our interest in looking at alpha equivalence modulo axioms. So the issue is that usually not all constructors are free. So if you want to, for example, specify the pi calculus, you need to say not just that the nu is a binder and you need alpha, you also need to say that the parallel composition is associative and commutative. The sum is associative and commutative. So you need to work with, if you're interested in unification or rewriting, you need to work modulo all these axioms. So the question is, do these combine well with alpha? Is it still decidable, efficient, etc.? So we looked, because in particular, as I said, we are interested in specifying first-order logic and process calcula that have AC operators as well as binders. We looked at combining the unification modulo alpha, nominal unification, with unification modulo axioms, which has been studied for a long time. It's called E-unification. If you don't put any restrictions on the theory E, it's undecidable. So there are equational theories for which you can't define. It's not surprising. It links with Hilbert's 10th problem. So it's undecidable in general. But for the cases that are more interesting for us, like commutativity and associativity and commutativity, there are unification algorithms. These cases are decidable. So we did look at unification modulo alpha and E, and if E can be defined by a rewrite system, you can implement nominal rewriting as a way of finding the unifiers. But the question now is, how about C and AC, which are the cases where you don't really need narrowing in first-order syntax? You can apply standard algorithms. Can you apply those if you also have binders? So you can. So the conclusion was that you can do it, but there are some surprises. So what does it mean that you are unifying modulo C, modulo commutativity? It means that when you apply your simplification rules, in particular the decomposition rule, you know, when you have f of s equal f of t and you say s equal t, if your root symbol is OR, you can decompose and unify the first argument with the first, but you could also unify the first argument with the second, which is what we are doing there in that OR, in that unification problem. We unify the first argument on the left with the second on the right, and then we are left with this equation on P, which we can solve provided that ABX is equal to X. Now, in the syntactic case, that's easy to solve. You just need A and B to be fresh for X. But when you have a commutative operation, you could have an equality even if A and B are in X. For example, you could have A plus B, or A or B, okay? And there, A and B are free, so they are not fresh, but the swapping of A and B in A plus B gives you B plus A, which is equal, okay? So you have a solution. Indeed, you have infinite solutions for this equation. The problem here is no longer finitary. So in syntactic unification, syntactic modulo C, it's finitary. You don't have one most general solution, but you have a finite complete set of unifiers. For alpha, it is unitary, but the mixture of the two give you a zero-ary unification problem. It's not even infinitary. It's not that you have an infinite complete set of solutions. It's that there is no infinite complete set of solutions. There is no complete set. You just have to enumerate infinite unifiers, which is not great. But then this is all relative, because you know the classes of the unification theories depend on the way you want to express the solution. So these classes are unitary or finitary or whatever, because we are expressing the solutions in a particular way. Here, we want to express the solutions with a substitution and a freshness context. In the syntactic case, it's just a substitution. What if we find another way of expressing the solution? And that gives the clue to what the good way of expressing the solution is, which is, instead of a freshness context and a substitution, we allow also what we call fixed point constraints. Because that equation there, what it's telling us is that X is a fixed point of the permutation AB, okay? So if you do allow that, then that's your solution already. So the problem is no longer zero-ary with that representation. So we did do that. We have a paper where we explain how to translate from freshness to fixed point constraints and get a finitary algorithm. And that problem doesn't happen if you're only interested in matching. So nominal matching, nominal C matching is finitary. For C unification, as I say, if you insist on using just substitution and freshness, then you will have to put up with these infinite unifiers. But if you are happy to use fixed point constraints as part of the solution, then it is finitary. Okay? So that's for C. For AC, things are complicated again. AC matching, it works. So AC unification in the syntactic case boils down to solving the Diophantine equations. I don't know if you're familiar, if you've ever seen Stickel's AC unification algorithm. It's one of the most popular ones. It's well known that to solve an AC unification problem, you need to solve a Diophantine set of equations, which it's normally in the decidable class. So AC unification is decidable. But the problem with the nominal AC unification matching is that, again, there is an interference. We believe it is decidable, and it would be also finitary, probably, using these fixed point constraints, but that's still work in progress. And it's work in progress that we need because we are interested in extending mod with nominal features, so that mod, which is a first-order rewrite language, can easily express languages with binders. But mod uses AC operators routinely, so it's good that we have AC matching and AC unification. As I say, nominal AC matching works well. We have a formalized algorithm in PVS. For unification, still to do. Okay, so I'm going to finish with this summary. You see, when I was telling you at the beginning that I really like PPDP and Lobster, many of these results I mentioned were presented in PPDP and Lobster, some almost 20 years ago, nominal rewriting. The quadratic lower bound was in 2010. Sorry, quadratic complexity. An algorithm of quadratic complexity for nominal unification was presented in Lobster, but we don't know the lower bound. That's a conjecture I mentioned before. We have some work that I didn't mention on adding types to these systems, and some extensions. Nominal C unification was also presented in Lobster. First, the decidability, then the algorithm that enumerates the infinite solutions. And last year, we defined matching logic with nominal features. Matching logic is the basis of K, the verification programming language verification framework K. So we added nominal features there, and still working on the extension of rewriting logic with AC. There are implementations of the algorithms I mentioned. There are some libraries, nominal libraries, one for Haskell, implemented by Jamie Gabay. If you go to the nominal project of the University of Brasilia, you can find the formalizations in PVS and some in COC of the algorithms, alpha equivalence check, matching, unification, also modulo C, and also matching modulo AC. If you're interested in nominal versions of Prolog, I would recommend looking at James Cheney's website. James and Christian implemented a version of Prolog with nominal features. It's called Alpha Prolog, and there's also a model checker attached to it. I also mentioned nominal Isabel, which you can find, again, if you go to the Isabel page. And I think that's all. Thank you.
Questions?
Hi, do you know what the situation is for theories, I don't know what you call them, where variables can disappear, where you have like inverses, say Boolean rings or Abelian groups?
So we are, at the moment, still trying to solve the problem with AC, okay? So what the solutions we have right now are, if you have a theory, like for Boolean rings, I think you can define a theory which is a representation which is based on a set of confluent and terminating rules. In that case, you could apply narrowing. We have nominal narrowing. And under certain conditions, it even terminates. So Santiago was working on, for example, finite variant narrowing, versions of narrowing that can make things easier. So at the moment, if you have binders and operators that satisfy the equations of a Boolean ring, the only solution I could say is try to use narrowing. But we are working on AC, and hopefully after AC, we will go to AC and unit and do a bit more. Okay.
Yeah, hello, thank you. Very informative, interesting talk. I've just got a comment, and I'm not really sure whether it's relevant in the context of the aims of your work. But if the complexity of unification is linear in the size of the terms being unified, in the context of a computation, the size of terms may grow unbounded. which is of course why Prolog has by default not implemented the occurs check, because you want unification to be more or less constant time, or depending only on the size of the rules or the program that you put in. So do you envisage that if nominal logic is used as the basis for a programming language, a practical computing system or proof system, that you would need to have something similar to dropping the occurs check?
Yeah, if you want it to be almost constant, like you say, yes. The algorithm is very, very similar to the first order one, because the extra complexity, which is these permutations, basically, you can deal with it with a good data structure to represent the permutations. So you need to be able to quickly find the image of a name, the inverse, and compose these permutations. So we have a good way of doing that. And the rest is just, you need the same ways of avoiding the explosion in size. So we have the same kind of data structure as you would use in a first order language, the same problem with the occurs check. So yeah, so I think in that sense, it should be similar, which is why the alpha Prolog works like Prolog. Mm-hmm. You don't really see a difference.
Yeah, it's often seen as a criticism of Prolog that.
Yeah, well, it shares, the nominal Prolog shares the same advantages, the same criticisms, yeah.
Thank you. Oh, this is only a technical question. I'm not an expert of the field, so when you design the algorithm, the unification algorithm, I have in mind, for example, the Milner algorithm for ML types. Well, what you do is, in that case, what you do is to generate a set of equations, and then eventually when you have the whole set produced, then you try unification and so on. In this case, you have something more because you have the freshness condition. So probably you generate not just equations, but sequence somehow. So how do you, my question is simply, how do you keep track of this essential constraint? Without it, it will be perfectly unsound, anything.
It's an excellent question. So when you are applying your simplification rules in the unification algorithm, avoiding explosion of things using pointers, etc., like you would use in Patterson's or with the Martelli-Montanari with the multi-equations, etc., you will generate these freshness constraints. So to keep the complexity down, you need to make sure you do several things. First, have a very good data structure to represent these permutations. Second, I told you permutations suspend on variables when I said that. In the algorithm, they suspend also on the top of the term. They are lazy. So you don't apply the permutation all the way and suspend on the variable. You suspend it on the top of the term and only apply this permutation if you really need it at the end, okay? Because otherwise, each time you have a permutation, you have to traverse the term to the variable leaves. We don't do that. We treat permutations in a kind of lazy way. We accumulate all the freshness constraints. In fact, what we accumulate is for each variable the list of atoms that need to be fresh. And at the very end, we do all these tests at once. So yeah, so the algorithm is not trivial. It's Christophe Calvet's thesis. He did both the Martelli-Montanari version and the one with graphs for the nominal terms, okay? And he also was the one that proved the complexity of the matching. So that table I showed you is all part of Christophe's thesis.
Any more questions? Well, I have, we can talk later. We have talked several times. So, I mean, just to say that as an expert in mod, as an expert in unification and also as an expert in cybersecurity protocol analysis. So I think that it is very important that you continue, okay? And there are many possibilities, okay? And as we, yes. And I will have this coming that many times. So I mean, all these advances that you keep doing, okay, are essential because indeed, I mean, these bindings are everywhere, as you showed at the beginning. Okay, so
Thank you so much.
Yeah, you're welcome.
Thanks.
So let's end, Maribel.
This one? No.
Yep. Yeah, okay. Welcome to the first Lobster talk, the short presentation. It will be on certified proof checkers for neural network verification. And the presentation will be given by Remy. Thank you very much.
Thank you. Hi, everyone. So, as the chair just introduced, my name is Remy, and I will present our ongoing work on implementing a formally verified proof checker for neural network verification with the Imandra theorem prover. And this is a joint work with Omri Isaac, who was supposed to come here but unfortunately could not join us today, along with Grant Passmore, Catherine Stark, Katja Komenenskaya, and Guy Katz. And for disclosure, Grant Passmore is the co-founder and co-CEO of Imandra, and Imandra funds my research as well. So first, let's start with asking ourselves, why do we need to verify neural networks? And why do we need proof checkers for neural network verification? So as you may well know, deep neural networks, or DNNs, have accomplished groundbreaking results in many safety-critical fields, like autonomous vehicles, autonomous aircraft, medical imaging. But their decision process is opaque to humans, and they are known to be sensitive to input perturbation. So small changes in an input of a neural network can cause large variation in the output of the network. So in order to mitigate this vulnerability, the verification community has been developing analysis tools for deep neural networks called verifiers. But these verifiers themselves are complex pieces of software with a lot of optimization in order to scale to the huge size of neural networks. And so they are also susceptible to having bugs in them. And in particular, Gia and Renard have shown that even a neural network that has been certified by a verifier can have an unsafe behavior because of the use of floating point arithmetic, and so it introduces numerical instability. To check the DNN verifier's result, some of them have implemented a proof production. So implementing a proof is a technique that's been widely used in SMT solvers, and it allows an external tool, the checker, to check the proof externally, and so to add trust to the verifier's result. But then we can ask ourselves, how do we trust this checker? It's itself a piece of software susceptible to bugs. It contains optimization because the size of proof can also be large. But this kind of reasoning opens the way to infinite regression. And in order to cut this short, the answer is to implement a trusted checker, so using a programming language that enables the use of formal methods to formally prove the correctness of the proof checker. And this is exactly our aim with this work. So we implement a novel proof checker for DNN verification, which improves on the existing implementations by offering numerical stability and formal verifiability of the proof checkers' correctness. We have also specified the checkers' correctness properties, and we've started to verify the checkers' compliance with this specification. And in order to implement this verified proof checker, we used, as I mentioned, the Imandra theorem prover. So the goal is to find a trade-off between scalability and trust and verifiability. And Imandra offered, for this use case, a good balance between the two. So its logic is based on a pure higher order subset of OCaml. So it gives us a higher order programming language, but also offers the ability to formally reason about the OCaml code or the Imandra code with proof by induction and numerous proof automation techniques. And in the end, we also have the ability to extract the verified code to native OCaml, so to benefit from the native OCaml compiler. So this is good for the scalability. But before I go more in detail in the details of the proof checker, I will talk about DNN verification and what type of proofs are being produced. So to give a brief overview of neural networks, they can be represented as computational graphs, where the input of each node is computed by computing the weighted sum of its parents, and then we apply nonlinear activation function. Here we will focus exclusively on neural networks with the ReLU activation function that's defined here, because it has good performance and it has the benefit of being piecewise linear. So it's easy to reason about. And in a second, we'll see that we had a refinement to this representation. We split the nodes with a ReLU activation function into two sort of subnodes. One is just the result of the, can I point? Sorry. Yeah, one is the result of the weighted sum of the parent nodes, and then the second one is just the result of applying ReLU to this B3 node here. So DNN, the problem of DNN verification is the aim is to decide, given a trained DNN n and a property p over the input and the output domain of the network, whether there exists an input x such that p holds. P is typically undesired property, so if we find a satisfying assignment x, this x is considered as a counterexample and the network is considered as unsafe. And as I mentioned, we consider DNN with piecewise linear activation function, and this allows us to formulate our verification query as an ensemble of linear and piecewise linear constraints. So here we have a representation of verification constraints. We have a neural network a property, a safety property. So the network is encoded in linear constraints with bounds for all the variables. And then the ReLU activation functions are encoded as piecewise linear constraints. And so very broadly, the algorithm uses linear programming to try to solve the linear constraints. And if it cannot find a conclusive result, it will split the piecewise linear constraints and create subqueries with the added information from the piecewise linear constraints. And so this creates a tree search, a tree structure for the search of the algorithm. So the result in each leaf of the tree is determined by the LP solver. Now onto the proof production. So we rely on previous works by Omri Isaac and colleagues, and they use the Farkas lemma to produce proofs for an LP solver based on the simplex algorithm for DNN verification. So the linear constraints that I showed earlier are normalized and encoded in a matrix called the tableau. And we try to find an assignment for the variable vector x bounded by the bound vectors L and U such that it satisfies the constraints encoded in the tableau. And in particular, they show, sorry, I can see that it's not very readable. But in particular, they show that if the problem is unsatisfiable, there exists a vector of coefficient, a column vector W, such that for all variable vector x with bound NLU, the linear combination of the tableau rows with the coefficients in W is bounded by a strictly positive upper bound. So the result is strictly of the linear combination scalar x is strictly negative. And so thus, W is a proof of the constraints system unsatisfiability. And moreover, this vector can be constructed during the execution of the simplex algorithm. And what the existence of this Farkas lemma allows us to do is that we can check the result of the simplex algorithm in linear time. Instead of having to rerun through all the steps of the iterations of the simplex algorithm, we can multiply or compute the linear combination of the tableau rows, check if its upper bound is negative, and we know if the result is valid in linear time. So the proof certificate matches this tree structure from the initial query. It contains all the information of the initial query, the tableau, the upper bounds, the lower bounds, and then the proof tree matches this search tree with each embranchment corresponding to a split over piecewise linear constraints. In the nodes, there are information that I won't go into details in now, but that refer to the dynamic bound tightenings. And so in the leaves, the vectors from the Farkas lemma that I just introduced are stored and allow us to check the proof. And so the proof checking algorithm consists in traversing the tree and checking in the non-leaf nodes if the split are correct. And again, I'm not getting into too much detail here, but checking that the bound tightening lemmas are correct. And more importantly, in the leaves, we check the contradiction vector, we compute the linear combination of the tableau rows and check that its upper bound is indeed negative. And if all the leaves if the proof checker checks that the Farkas lemma are correct in all the leaves, then it means that the proof is correct. This is for the case where the problem is not satisfiable. Of course, if the problem is satisfiable, then the simplex algorithm just gives us a satisfying assignment, and it's straightforward to check if it's valid or not. So now we can arrive at the implementation in Imandra of this proof checker. So here we can see what Imandra code looks like. So we can see that it's a valid OCaml syntax, as it's just a subset of OCaml. And so what we did was adapt the existing proof checker implemented in C++ into the Imandra's functional programming language. And this in particular shows the definition of the class for the C++ implementation and the type for the Imandra implementation of each proof tree in the proof certificate. And one thing that we can already see here is that in the Imandra implementation, the structural correctness of the proof tree is guaranteed at type level, so we don't have to have a valid function that checks if the structure is valid or if the proof tree has all the necessary information. As I mentioned earlier as well, Imandra supports arbitrary precision real arithmetic, which allows us to avoid the numerical stability problem. It does so by using a native OCaml library, which itself is an interface for the GMP library. And so this part, the GMP library, is not itself formally verified, but it's well tested and standard enough that we're happy with having that as part of the trusted code base. I'll go quickly over these, but basically the fact of having a high-level language, basically OCaml with theory for reasoning about standard data structures like lists and maps, allowed us to experiment with different data structures. So the standard inductive definition of lists in OCaml, but which was better for the verification that I'll mention in a moment, and then an implementation of sparse lists that are implemented as binary trees. Again, going quickly over this, but we also it also allowed us to experiment with different verification mode, which allows us to balance between scalability and trust. And in the end, we evaluated our implementation on a number of examples from the ACAS-XU neural network verification benchmark. So proofs generated by the Marabou proof checker on examples from the benchmark. And from what we saw is that so we compared with the existing C++ implementation of the proof checker, and from what we saw is that our best comparable version of the proof checker is less performant than the C++ implementation, but that was expected because it wasn't as optimized as the C++ implementation. But it was a linear overhead, so that was quite satisfying. And we can also see that there are definitely optimizations to be made because, for instance, the sparse vector implementation is faster for a mode and slower for the other mode of verification. So we know we have avenues of amelioration. Now I will present the correctness specification and how we verified the first part of this correctness specification. So to go back to this definition that I gave earlier, so what we want to prove is the second part, the unset case of this theorem, is that in our implementation, if the linear combination of the tableau rows has a strictly negative upper bound, then the constraints are indeed unsatisfiable. And to do that, we started with using the same representations of the tableau as a matrix as earlier, but it turned out that it was easier to redefine slightly the problem, and so switch from a matrix-based representation to linear polynomials. So we give definitions for the linear combination and positive linear combinations of polynomials. And now we consider a system S with normalized equalities P1 to Pm and inequalities with polynomials Q1 to Qn. And what we want to prove now is that if there exists a linear combination I of the polynomials Py to Pm and a positive linear combination C of the polynomials Q1 to Qn, such that I plus C is a strictly negative constant, then S is unsatisfiable. And the proof of this goes as follows. So retaining the same notation as before, if we have the linear combination and the positive linear combination of the equality and inequality polynomials I and C, such that I plus C is strictly negative, then the polynomial function I plus C, or the evaluation of I plus C, is strictly negative. And on the other hand, the propositions in S imply that I of x is equal to 0 because I is defined as the linear combination of P1 to N and P1 to M are all equal to 0, and similarly C of x is greater or equal to 0. We then have that I plus C of x is greater or equal or is positive, so this leads to a contradiction, and so this is a proof that S is unsatisfiable in this case. And to prove this, we define the theorem we want to prove in Imandra. So the arguments to the Imandra function are implicitly universally quantified. We have S the system, X the variable vector, C is the vector of all the coefficients for for computing I and C. Well-formed is just, so we have a Boolean valued function with an implication. So in the preconditions, well-formed means that the dimensions of all the structures are coherent, so that Imandra doesn't consider empty lists or whatnot. And check certificate computes that the linear combination I plus C is strictly negative. And eval system it just checks that the variable vector x satisfies the propositions in S. So to prove this theorem quickly, first we prove the first part of the theorem. So if I plus c equals 0, then the evaluation is strictly negative. Here we can see the annotations, the guides that we give to Imandra to prove this. So there are other lemmas that were defined outside of the functions, but they're automatically called and applied by Imandra. So this is all we need to give to prove this lemma. Then we prove the second part of the lemma, and finally we use again this annotation applied to use the two previously defined lemmas to prove the main theorem. And so in total, the proof for the correctness has 15 lemmas and 233 lines of code, which we thought was pretty succinct and elegant. And to conclude very briefly, so we proposed the new implementation of the proof checker for DNN verification. Our implementation offers better numerical stability, greater verifiability. We started to specify the correctness property and to verify it. Now there are other parts of the proof checker that we still need to verify, in particular the dynamic bound tightening lemmas that I mentioned briefly. And so this is ongoing work. And in future work, we also aim to optimize the performance and integrate the verification of the neural network with the verification of a larger system that contains machine learning enabled components using this proof checking facility. So that's me. Thanks for your attention. I'll be happy to take any questions.
Hi, Thomas Jensen. Farkas lemma has been used to also to certify program analysis, like to produce certificates for polyhedral analysis in the past. So in my group, we use this to do to build a proof carrying code framework where you use Farkas lemmas and the witnesses that you get there to certify this. This was built in COG. Did you consider using that instead of starting all over?
I actually, I didn't find, I looked for implementation of the proofs of Farkas lemma in different theorem provers, and I found the Isabelle Hall one, but not the Koch one, so I'd be interested if you could share it with us.
Yeah, it's online. It's there's one in Rieren, and I think the David Monio's group in Grenoble also built one. So
all right. And we considered using Koch, but first, I'm not a specialist in Koch and I have little experience in it. But from what I saw, the advantage in using Imandra is that we had expertise in programming in OCaml, and so we could directly leverage that to implement the algorithm and verify it in the same environment, if that makes sense.
So it would be interesting to hear the comparison of the two approaches.
Yeah, that would be very interesting. Thanks for the suggestion.
Thank you.
Other questions?
Okay. So it's a minor technical question that in the eval system, when you were evaluating this set of constraints, did you define your own evaluation or did you use the native data structure of the theorem prover that you are considering?
No, so we implemented our evaluation function, and one thing that I did not mention is that the evaluation also checks that the coefficients for the more in the check certificate function, we also check that the coefficients for the inequality polynomials are positive. So we all define it's all defined.
Correct. But my question is more about like eval system SX. Is that something that you you defined what it means to evaluate it, or did you use do you convert it to native data structure of the theorem prover that you're using?
So. Right, I see what you mean. So in fact, we're using mostly native data structures. So for instance, here the system is just a type alias for a list of a native list of expressions.
Okay.
And so we use native data types.
More questions? Yeah, then maybe I have a question. Looking at this slide with the 15 lemmas and 233 lines of code. Would you have an intuition? You show it's 15 lemmas, 233 lines of code. Why it is so elegant? To what it can be attributed?
Good question. I think that since Imandra already has a lot of lemmas for operations on lists and real arithmetic, we didn't have to redefine any. And since we're using the native list data type, we didn't have to redefine any of the properties for that. For instance, I know that a lot of lemmas for the length of the list are reused so I think this is taking advantage of a lot of Imandra's proof automation. Also, one thing I noticed with using greater automation with Imandra is that we arrive at very short proofs, but compared to the small experience I have in Coq, it's sometimes harder to figure out which lemma is missing to advance the proof. But once you figure it out and you know where Imandra is trying to advance the proof automatically, and you know which element is missing, then it can be quite elegant.
Yeah, thank you. Other questions, comments? Yeah.
Thanks for the talk. So you have a proof of Farkas lemma, but do you relate it with a proof about something in the DNN?
That's a very good question. So what we relate it with the proof checking algorithm that checks the proof in the DNN. So the check certificate function that it's the main function that we verify here, for which we verify the correctness, and this is the one that's used in the main proof checking algorithm that's defined. And so this proof checking algorithm it verifies that the property over the DNN holds via basically in the system, the polynomials for the linear constraints encode the DNN, if that makes sense.
Other comments or questions to our speaker? Yeah. If not, then let's thank our speaker for an interesting. So this is the end of the first Lobster session. We continue in the afternoon with 2 more sessions. Today, the last session will feature the Best Paper Awards. And tomorrow we continue with 3 more sessions, and the first session tomorrow morning will be an invited talk by Manuel Remenegildo on using abstract interpretation. So I'm looking forward to see you again, and enjoy the lunch. Thank you.
welcome everybody to the first research session of Lobster this year. So welcome to the first research session of Lobster. So after the nice invited talk this morning, and we start with a paper on reusable machine calculus for automatic resource analysis, and Hector will present it. So please go.
Thank you very much, and thank you for having me. So, hi, my name is Hector, and I'm going to present the work I did to create a reusable calculus based on the stack machine for automated resource analysis. This is work I did with my PhD advisor, Emmanuel Chailloux, at the LIPSIS, the computer science lab at Sorbonne University. So, what are we talking about here? So, resource analysis, as far as we're interested in it, we want to figure out how much material resources, so time, memory, or energy, is used by a program written in a high-level programming language like ML or Haskell. So the problem is to recover operational behavior from those, from the source code of those programs, while those languages really try to hide that from you. The approach we've taken is to use an abstract machine, which we hope is a good first bound between software and hardware, but also is sufficiently neutral to allow for portable analysis. And as we'll see, the main feature we're using is first-class evaluation contexts, and I'm going to talk more about that. At the end of the day, what we achieve right now is some functional imperative programs with explicit allocation and freeing of cost, and our analysis is implemented as an effect system for those programming languages. So what we're going to talk about is first what are the main techniques for resource analysis that we're going to use, and we're going to present our tool in a general sense. Then we're going to talk about the abstract machine ILL as is, then how to encode more traditional programming languages in the machine, and then give an overview of what everything looks like at the end. So, automating amortized analysis. So what are we talking about when we say amortized analysis? So if we consider this code that implements a functional queue, hang on, I'm going to put a pointer here. Yes, okay. So we implement a queue with a pair of lists. So we have a front list that represents the back of the stack. Well, we have a back list to represent the back of the stack, and a front list to represent the elements that are on the front of the queue. So when enqueuing an element, we just push it to the back of the queue. But when dequeuing, if we have someone at the front of the queue, we just pop that off. But if we do not, first we reverse the back of the queue to the front, and then we dequeue this. So if we're interested, for example, here in the amount of time we call the constructor for lists, what we see is that dequeue makes a call to reverse. That call to reverse makes n calls to cons, where n is the size of the list being reversed. So if you process n elements through the queue, we should get some quadratic complexity. But if we look at it in a finer way, we find out that every element is only flipped once, is only passed through reverse once. So in actuality, this code has linear complexity, and it's quite important in that case. And what we'd like to do is to undertake those reasonings automatically. Here, what we're going to do is say that if we pay the cost of 2 every time we enqueue an element, we can pay one cost for the reverse and another one for the cons right here in the enqueue, which will be enough to get the result we want about linearity. So how do we formalize that? We formalize it by saying that programs are command C, which reduce their small step semantics. At each step, we accumulate a cost, which can be positive if the cost is paid, or negative if some resource is reclaimed. At the end of the day, what we get is the cost of the program is the maximum partial sum over the entire execution, which represents the instant at which most resources are allocated at the same time. So to get a bound on this reduction, what we do is we fix a potential function on commands, which can cover every single cost, and then the initial potential is a compiled time bound on the cost of the overall program. The problem is, in order for this to work, we need our commands to be built out of value, which is a program we are computing, so a function basically, and it interacts with an evaluation context called a stack, which contains arguments for the function. And we know V, that's a program whose source code we have, but we don't know S. What we're going to do is we approximate this unknown parameter stack with some variables representing size and length of arguments, and at the end we want to instantiate some function p of n as our potential. So the way we do that, this can be done automatically using a technique called automated amortized resource analysis. The idea is to enrich the typing disciplines on functional languages with parameters at type level to represent length and size. Here, this list of 3 integers has length 3, and that's indicated in the types. So preserving the amount of resources allocated in 3 in the program gives you a constraint on those type level parameters at each point in the program. And you can accumulate those and eventually get a program-wide constraint on parameters. What you do is you try to solve this constraint in some consistent but not complete way to get some system of equations that you can eventually optimize to get a bound. For example, using standard HARA techniques, we can figure out that if n elements are processed, we do get a linear time for the functional queue we saw earlier. A recent formalization of HARA that we think is extremely important is given by Lambda Amor, which was presented a couple years ago. And this is a lambda calculus with an affine type system. So you can take into account resource flow in the program. And it has a more mainstream type system than previous implementation, in that we have normal types and parameters, let's say integers, and we have dependencies of type on parameters. And in Lambda Amor, this potential function that we want to build is split over all potential values currently in scope, and so each value holds its own potential. The way we encode this potential is using the type bracket p of t, which is some value with potential p. We have the type m p of t, which are computations that will incur a cost p, and then we have quantifications over parameters and manipulation of parameter constraints. Here this is implication and witnessing that some constraints hold. So the functional queues that we saw before can be expressed here by saying that a queue is data structures with 2 parameters p and q, whose sum is the full size of the queue, and the queue is a pair of lists, one of size p, one of size q, and it must hold 2p plus q potential to cover for its processing. So you can see here that the 2 lists have heterogeneous potential. And the type system of Lambda Amor lets us encode that at type level. So how are we trying to, so what are we doing how do we implement this in our system? So, so the main problem that Lambda Amor has that we're trying to solve is that there are no universal small step semantics for lambda calculus-based languages. So if I just look at function application, if I reduce it in call by name semantics, I just substitute the body of the argument. I just substitute the argument in the body of the function. But if I want evaluation in call by value semantics, I have to first evaluate the argument with continuation the body of the function. And if we pick one of those systematically, we can get eager versus lazy evaluations, but we'd like to be able to mix and match those evaluations to get some lazy monadic computations, to work with some iterators, and and work with some iterators to cover a larger body of functional algorithms in our programs. The reason this is complicated in current resource analysis system is because we can understand potential and resources using parameters that are put on types, which recover some structure in the data manipulated by the program. So a list has length, a tree can have depth and width, but in lambda calculus, computational contexts are not data. So we cannot use the same system to say this iterator will be called in that way, or this monadic action will be used in that way. And that's a problem. So what we do to resolve that issue is to use a defunctionalized continuation passing machine, meaning that the stacks that we talked about become just more data structures, and they can now be analyzed with the same techniques that Hara has developed to infer parameters on data structures. So Autobill is the project we implemented. It's a modular framework for automated resource analysis, and it supports main input languages. So a OCaml-like programming language with call-by-value semantics, but also a call-by-push-value lambda calculus, and directly the machine with explicit parameter types. And as opposed to previous implementations of Hara techniques, we support arbitrary first-order parameters, meaning that you can define your own sorts and operations on type-level parameters and get a first-order constraint out of those. And it is available, it is open source software. When we try to imitate previous Hara work, what we get is parameters are integers and functions on integers that are modeled by multivariate polynomials with integer coefficients. And in that setting, we can reduce the constraints to some algebraic problem that we can solve using the Minizenk solver suits, which give a pretty user-friendly interface to solvers and optimizers. And so we can recover the simple results we have for the functional queue. So how does this work? First, we have our input language, which is some kind of a functional statically typed lambda calculus. And the first thing we do is we translate it to call-by-push value evaluation, which gives us an explicit notion of control flow for the program. So the call-by-push value program will somehow embed its own operational semantics. Then we run a CPS transformation, which gives us our abstract machine notation. On this abstract machine notation, we can run a linear type inference algorithm, which can explicit data flow. So when is data shared? When is it just forgotten about? And finally, we can run our effect system, which turns cost primitive into resource manipulations. So resources are being threaded into the entire machine at each step. And then we just run parameter inference to get a constraint and resolve the constraint using some solver if some solver is available for the theory that is used for the analysis in question. So what is this abstract machine and how do we capture computational contexts? So the machine is based on work by Curien and Al. So to study the computational interpretation of intuitionistic linear logic, and it's a machine with call-by-push value semantics, which means it has a thing called polarized evaluation. So what that means is there are two sorts of base types. There are data types, like data structures, which are evaluated eagerly, and there are computations, like functions and funcs, which are evaluated lazily. So we extend this machine with parameter polymorphism, with explicit sharing for tracking data flow, and some fixed points to represent loops and iteration. So the machine is either some data being processed by a stack or some computation consuming some evaluation context. And the values so far can be variable and binders on each side. X are value variables and alphas are here are stack variables. And you have the obvious reduction in which when you bind something with a name, you just substitute the name. The polarized thing comes into play when we try to evaluate some ambiguous command here. So which of the binder wins? Well, if A and X have positive polarity, what happens is the data side wins, which lets you evaluate expressions that consume their computation context and produce some data. And if the polarity is negative, the computational context win and can process a computation before the computation is run. And this disambiguation is the key that lets us manipulate evaluation context and get unambiguous operational semantics on the machine. So what data structures look like is this. So we have here a data type definition for linked list. So it's a list of size n with element type A, and A can depend on its position on the list. So it's of sort natural number 2 parse, which is the sort of data. And the list is either a nil constructor, which holds no element and has size 0, or it is a node in the list, which has an element of type an, and a tail of the list, whereas a tail has size m, and we have a constraint that m plus 1 equals n. And we write it this way instead of n minus 1 to avoid the problems of subtraction not being quite a total function on natural integers. So in type definitions, we can introduce new parameters here with a where clause and introduce constraints on parameters which must be witnessed when some constructor is used. So we had to values this constructor with arguments, which witnesses that parameters exist and constraints are satisfied. We have pattern matching, which is classical pattern matching, but it will introduce universally quantified parameters. Universally quantified parameters on which the constraint is assumed to hold, and during reduction, whichever parameters were typed here are used to instantiate the universally quantified parameters there. And using those data type definition, we can recover many types from lambda armor, including linear data structures, quantification, the existential quantification over parameters, and witnessing some constraints. On the other side, we finally have our explicit computational context. So the idea is that our stack, which is data representing the context, is just a list of stack frames, so a kind of data structures. And a computation is just a thing that captures and matches on that data structure. And that gives us functions, lazy pairs with projections, as well as universal quantification. So here, for example, I have a stream data type, which will produce values over and over, and the stream is indexed by the number of iterations we have already done. So if we step once inside the stream, what we get in return is a value of type an and a new stream, which when called will produce a new value of type an plus 1. And as far as syntax is concerned, stacks are exactly constructors with values pushed on top of another stack, and computations are just things that pattern match on that stack to uncover one frame and capture the rest of the stack as a continuation. And so with that, we can recover the two sides of lambda armor with our call by push value semantics. We finally just had exponentials for sharing and fixed points for recursion. So in resource analysis, surprisingly, linearity we found is not as important as polarization, meaning that linearity is only required for resources, so for resource-bearing data. If resources do not hold potentials, if data does not hold potential. It can and should be shareable freely, but only resources need to be unduplicated. On the other hand, polarization is very important because this is what defines the evaluation order of the program, and so which cost profile it's going to have. So we just had exponential. So this value ln alpha is in C is a shareable value which will produce a linear value, which will produce and return a linear value to a continuation alpha. And on the other side, once a value has been shared and duplicated, we just use a continuation ln on top of a stack S to produce a linear value and feed it to continuation S. And we use the same, and we also fill out fixed points for recursion. So fixed points in the calculus are just terms that satisfy the fixed point equation. In an abstract machine, this just means that a fixed point is a value which is equal to itself applied to a certain continuation. So we just use that on the nose and say that a fixed point is a value in which self is applied to a continuation and then fed to some external consumer of that fixed point. So with this setup, we can manipulate our parameters, share values with those parameters, and consider iteration, and we have some consistency on which on the approximation we make of parameters at compile time. So typing judgments in our machine look like, so they have a parameter context, in which context have a type. They have a value context, in which the type of values is dependent on the value of parameters. We have a continuation context, which is also parameterized, and a command as a parameter context, a first order constraint on those parameters, and then variables and a continuation. And this means that for every assignment of parameters in thetas that satisfy constraint C, and variables that are typed in accordance with that, the command is well typed. This command is well typed, and this is preserved in some sense by small step semantics, in that if a well-typed command reduces to another well-typed command, then we have this implication for every parameter. And this is due to the fact that the machine corresponds to intuitionistic linear logic, and manipulation of parameters corresponds to the same manipulation done in sequent calculus and its proof of cut elimination, which we can reuse quite directly in our system. So now that we have this machine that can encode some kind of mix and match operational semantics and parameters, which can be approximated consistently, we can encode programming languages. So to do that, we just had some syntactic sugar to the machine, just saying that funcs are functions which takes, funcs are functions that takes no arguments, so of type 1 lollipop t, and they return some data t. And so the syntactic sugar is just some command with a continuation, and this command, when run, will provide its computed value to alpha. And so if we have some func on one side of the machine, on the other side we can either force the func and get the return value, or we can just bind it to a name x and manipulate it without running it. Likewise, closures are data holding computation, and if some context wants to open the continuation, wants to open the closure can just let itself be opened, or it can force the context to be dragged into its scope of definition so that the computation inside of it remains well formed. And with those two syntactic sugars, we can define, for example, callback value semantics for our machine, in which functions from A to B become closure that take some data argument A and define a func that, when run, will produce some data of type B. So expression in the language become funcs that return some data, and using what we saw to manipulate funcs, we can implement the operational semantics of call-by-value languages inside the machine. Not only that, but we also have an effect system for it for free. So if we look at this type here, if we just redefine closures and funcs, so redefining closure to take an extra argument of type S, and funcs to return an extra argument of type S, functions become state-passing functions that get a state as input and a state as output, which we're going to use to encode resource manipulation. We're just going to pass resources this way in this universal effect system that we get for free with the machine. So that's AutoBuild and the effect system for multi analysis. So what we do is we just define a data type, a state token with two parameters, P and Q, P being the free resources that the program has access to, and Q being the currently allocated resources. So, and we can define resource manipulation primitives just as constructors on that data type. So as the program begins, some constant amount of resources are free, and none of them are currently used. Then, when we allocate some value, we just move some resources from the free side to the allocated size, and we do the reverse when freeing those resources. And we also have some relaxation operation which can allow us to add in precision to our static analysis to make the problem easier to solve. And what this implementation gives us is that the total amount of resources used in the machine, available to the machine, stays constant as reduction evolves by definition. So we have allocation and freeing primitives which keep the total amount of resources constant, which greatly simplifies proofs of consistency for analysis, which usually have to do quite some work to prove that as data is manipulated, potential stays constant. And the problem of finding a potential function just become, given some ML, some lambda calculi with alloc and free put in, try to minimize this P0 parameter, which is used in the definition of the token. Finally, we can recover what lambda mode does with values in potential by saying that a shareable value that holds some potential phi of n is merely something that when given a token with phi of n used resources will freeze those resources, so make those resources available, and then we get a value without potential. And this notation lets us recover values with potential while staying correct regarding our state token. So the full analysis finally looks like this. So given a function from A to B, we translate it to callback push value with a continuation passing style, which makes evaluation strategy and computation context both explicit. Then using some linear typing, we can recover data flow through the program. Then we add our state token using the effect system. And finally, we type with parameters to get something that says a function works for every parameters n that satisfies some constraint C, and then we'll return some new state defined by some other parameters that satisfy another constraint. And the user of the function can choose which parameters go there, and the functions will return as well some parameters. So once we have a program gone through this entire pipeline, and we have these types, the question that remains is, can we go from this type with parameters and first order constraints to an explicit formula for complexity? This is to say, can we get some, here some polynomial that represents this, this complexity? So for some analysis we can, for example, for polynomial complexity in ARA, we have that every single implication we have in the first order constraint we have set up so that it looks like x equals some expression implies c, which we can reduce by substitution. At the end of the day, those first order constraints used by ARA look like a combination of polynomials, applications of polynomials, and using the two quantifiers, but only conjunction and equality. And we can solve that using some heuristic which was previously implemented for ARA, which is we scalamize every variable bound by an existential quantifier. So we take our x, so existentially quantified in some scope in which some variable y's are in scope. We build a new multivariate polynomial and substitute x for p of y. And once we do that for every quantifier, what we have is a system of equations, so a conjunction of equations on polynomial, and once we translate that to a system on their coefficients, we get some kind of nonlinear programming problems involving the coefficients a, k that we generated, and what we optimize on is a chosen ak, which is a leading term of the complexity of the whole of the program. So what we had at the end of the day is a new intermediate representation for type-based static analysis that can recover both call by name and call by value evaluation, and can be used to mix and match things with so to mix and match evaluation strategies, enabling uses of monads and iterators on in analyzable functional languages. This uses effect systems that we have built for it, and the good thing that we found is that we can factorize analysis by first solving all the semantic problem, going from the language to the machine, generating a first order constraint, and then separately this constraint can be solved, which means that if we want to add a new programming language to the analysis, we just have to redo the front end of the analysis, and if we want to add new complexity classes, we just have to upgrade the constraint solver separately, which was absolutely not the case for previous implementations of ARA as far as we can tell. There are still, of course, some open problems in that regard, which is one, we need good solvers for the kind of constraint generated by resource analysis. And also, if you want to represent fine memory management, we need some kind of region system or heap semantics for our programming language. Thank you very much.
So we have time for questions. Are there any questions? So, John.
Yeah, it's really rather than a question, it's a request for clarification in some ways, because you take your source language and then you translate it into something else, which may well preserve the meaning of the program, but where did you argue that it preserves the complexity? I mean, you rejected the operational semantics, which would be the obvious way to get something that you could analyze which corresponds, you expect, to the execution of the machine. But what you derive is something quite different from the original. And then you proceed to analyze that.
Yeah. So that's a very good question, and it's gonna be a problem, I believe, in every resource analysis system that attempts to work with many programming languages. So the way that we prove that consistency is preserved is by using an intermediate representation in which we have the machine and cost semantics without without our effect system. So we go from the source language, let's say a call by value lambda calculus, with cost primitives, and we go to the call by push value machines with cost primitive, and we show that this translation preserves complexity in that case, and then we have a second translation which elaborates our state token through the program, and we show that this is consistent regarding the second semantics on the machine. So this factorization is where it gets used. It is what helps us prove consistency for high-level source languages, saying that if you have a call by push value semantic, if you can prove that the translation to call by push value with resource primitive is correct, then we can go the rest of the way.
Okay.
Yeah, thanks for the talk. So one nice thing about ARA is that it can also be extended for not only amortized analysis, but also expected amortized analysis.
Expected in which sense?
For example, my algorithm might make random choices, and then I kind of have the average over that. So is this also applicable for your approach, or would this be a problem?
I do believe there is one problem when it comes to consistency is, so if we look at our consistency theorem, which is here, what we get is that, here this constraints gives also some kind of model for theta, so a set of assignment of theta which is valid for this constraint. And this applications tells us that models are included in each other. So the reason this works for resource analysis is that we're doing upper bounds, and that the values of P and Qs that make the program correct can only be extended as the program goes on. So that is to say, if we evaluate the program past its peak resource consumption, or past some hard to predict step of reduction, the bound will get, so the bound, okay, let me explain again. Approximation becomes more precise as you run the program. At the end of the day, if you run the program on, if you run the analysis on a completed program, you know exactly what resources are manipulated, but at the beginning you don't know at all. So you have a refined approximation. And in our proof, we use extensively the fact that as the approximation gets better and better, the bound that we get can get lower and lower because we're doing upper bound, and lower bounds basically means that models of bad approximation are included in models of good approximation, but I'm not sure if it works for average complexity. Yeah, it's yeah, we're getting up. Yeah, but we're just doing upper bound, worst case scenario, basically.
Okay, I have one final question because you can cover lazy as well as call by value semantics. Do you have examples where you have different amortized costs for the same program?
With lazy and
with
non-lazy,
lazy and call by value.
Yes. So, for example, if you take a list and you do a map, then filter on it. If you use call by value, you will generate the intermediate list, which you don't want. And if you use call by name, you won't do that because actually your lazy list will be some kind of iterator. And we can absolutely capture that in the system, and that's kind of the reason we want to have call by push value semantics, is we want to, in order to not have recursion all the time, we want to use iterators instead, which I believe are more tractable in general. So yeah.
Okay, thank you. Okay, so we run out of time, so thanks again for the discussion. So now we'll switch to the next talk. Okay, so here we see the title, A Logical Interpretation of Asynchronous Multi-Party Compatibility, and Sonia will give the talk.
Hi, thank you. So this is a joint work with Marco Carbone, who's in the room, and Carsten Sherman. And yes, it's about a logical interpretation of asynchronous multi-party compatibility. So the background for this talk is the Curry-Howard correspondence between the lambda calculus and intuitionistic logic, which has served as inspiration for many, many works. And it's been shown that there is a similar correspondence between session-typed biocalculus and linear logic. And we believe that by exploring this correspondence more deeply, it could also become a fruitful inspiration source. Sorry for my voice. So this correspondence between the session-type biocalculus and linear logic, I'm going to give you a bit more details. But it's basically established for a restricted part of this biocalculus. And so the main concept that we were interested to understand within that correspondence is the one of multi-party compatibility, as you saw in the title. So what is multi-party compatibility? It's a concept that has emerged in the multi-party session type community. So it's intuitively the fact that given a set of processes, they can communicate without reaching an error. They can you can put them together and they will live happily ever after. So it has been conceptualized by different authors in different ways. But what comes back as kind of the main idea is the fact that the computation path is live, meaning that every input message is eventually sent and every sending instruction is eventually executed. So nobody gets stuck with a message that needs to be sent and is not, or something that is sent and that is not received. So as I said, there are different formulations of this concept of multi-party compatibility, but they are usually based on the semantics of the processes. So you give the processes some understanding, some formal understanding of their behavior, and depending on how these behaviors compose, they will be said to be compatible or not compatible. So because we are working in this context of the Curry-Howard correspondence, we want to work in a very syntactic way. So what I will present today is a syntactic understanding, and in fact a logical understanding of this multi-party compatibility. So let me go back on the Curry-Howard correspondence for session types. So I'm not going to give any formal definitions, but mostly I'll mostly base my talk on examples. Session types are a way to give types to processes, communicating processes. So binary session types processes that communicate, that two processes that communicate. So for example, here I have process P1, which sends something, then receives something and closes, and P2, which sends something, receives something, sends something, and wait. And of course, the idea is that P1 will send this something which, I had animations which I forgot. So let me go back. So P1 sends something and wants to receive something. P2 receives something, wants to receive something, and to send something. And so, yes, so the idea is that it is possible to see the typing discipline on these processes in correspondence with linear logic. So we use linear logics connective as a result to read these types. So okay, maybe I can I point? No. Okay, maybe I cannot point. So the cross circle symbol is called a tensor, and it's used to type sending operations, and the reverse ampersand is called par, and is used to type is used to type receive operations. So because so if we say that this little variable a was of type A, and little variable b was of type b, again I cannot point and I cannot move from the mic. So we have some basic types A and B, and these are the types of the things that are sent and received. And these two types corresponds to the messages, the processes that are on the left. I hope it's clear without the pointing. Right. So the tensor corresponds to outputs, and the par corresponds to inputs. So, and the reason why we can say it's similar to Curry-Howard correspondence is because a proof in linear logic of this type will really correspond to a typing inference for the corresponding process. So by reading bottom up, we want to type this process. Okay, the image doesn't correspond. P1, yeah, it's P2. It should be P2. It should say P2 there. So the reception is this par operator, and then we can apply this rule, this par rule. Then the send corresponds to the tensor operator, which corresponds exactly to the tensor rule in linear logic, and so on. So the correspondence is not just the fact that the types can be written in this language, but it really is at the level of the proofs and type inferences as well. And then, similarly to the Curry-Howard correspondence, similarly to the Curry-Howard correspondence for lambda calculus and linear logic, the correspondence goes one level deeper, which is that so in lambda calculus, it's the fact that the lambda reduction can be seen as cut normalization in inductionistic logic. And here we have the fact that when we put these processes and have them communicate with each other, we can see this also as the cut rule, the cut reduction rule in the linear logic. So this was all previous work. So one thing to notice is that, okay, this is kind of a simple notion of compatibility. Here we have that these two processes, they can communicate because every send action is matched by a receive action, which is transferred to the type level by the fact that the two types are dual to each other. So tensor is dual to par. And so when we have a tensor something, or a tensor, the rest of the formula, and a perpendicular par, the rest of the formula, these two types are dual, and therefore the process can communicate. So it goes both ways. If the two types are dual, they can communicate. Right. So it is one simple case of compatibility. So this case of compatibility is the case where we are in the binary setting and the communication is synchronous, meaning that every send is happening exactly right at the same time as the receive. We can do it at the same time if we want. So again, as you saw in the title, the idea of this work is to generalize this to multi-party compatibility. And so multi-party means that we want more than two processes to communicate together. This has been studied a lot in the multi-party session, in the session type community by multi-party session types. And it has also been studied in the context of this Curry-Howard correspondence. So I will give you a bit more details on that now. Okay, so all the things that I said before about using linear logic for each single process works. The only question is, how do we compose them together? Because now clearly they are not dual to each other. The first process sends an A, receives a C. The second one receives an A, sends a B. And the last one sends a B, receives a B, sends a C. So they are using different types to communicate. But it's still clear that they can communicate with each other, that they are compatible. So you need to extend this notion of duality on types to something more that can account for this. So the concept that has been introduced by Marco and others is the one of coherence. So what does coherence do? Well, it does what you expect. It kind of matches it kind of does duality, but not throughout the formula, but bit by bit. So it just looks at the beginning of the formula, looks at it is dual, and continues. So before, when we were looking at dual types and in the binary setting, really the whole formula was dual. A tensor B power 1 is really dual to A power B tensor 1. Whereas here, we have this bits by bits duality. So we have, again, looking bottom up, we are removing one bit of the duality each time. So that is a condition that is sufficient to show compatibility of these two types and therefore of these processes. But as you can maybe see, that it kind of imposes this this fixed timeline, right? This fact that first we have to match the A's and then we have to match the B's, and so now we want to have a way to extend this, because these are not the only processes that are compatible. So now let me get into the other kind of axis of this generalization, is to look at processes that where we cannot do this matching in bit by bit. So namely, the communication has to be asynchronous. So if we have two processes, one sends an A, waits to receive a B, and another one sends a B and wants to receive an A, well, they can still communicate, because they could send whatever their message was in the network, and they could then receive what they were waiting to receive. But none of our preceding criteria was applicable here. So we can still give them linear types in a similar way. So tensor is still used to describe send, and par is still used to describe receive. But clearly, the two types now are not dual anymore. So we need again a way to show that these types are compatible. And so that means a syntactic criterion on these types that that shows that they are compatible. So the idea is exactly like I described informally, which is that instead of doing the communication immediately, you can store the message that is sent in a buffer. wait at a later time to be received. So we add these kind of stacks at the front of each formula, there of each type, to represent that fact that there is something that has been sent but hasn't yet been received. So then the two send operations can be done, and then the two receives operations can be done, and that's it. The processes are compatible. So our work is therefore here in this last corner. So we have a syntactic characterization of compatibility in the context of multi-party sessions and asynchronous communication. So again, we are in the same context where we can represent the types by these linear propositions, and all these processes want to send at the same time, and they want to receive afterwards. And so our criteria will be on these three types, a way to show that they are compatible, and therefore we can execute the communication in a correct way without reaching an error. Okay, so how does it work technically? Here we will again use buffers, but we need a bit more information in the judgment, in the type judgment, to be able to execute the communication correctly. And what it means is that each type here needs to be labeled by the receiver or the sender of the information. So here we have three operations. Okay, and one thing that is maybe a bit confusing is that we now have to flip all the types to their duals. Yeah, I didn't want to write something incorrect, but maybe I should have so that it would be clearer. So basically, we need to say that X1, process 1, which type B1, wants to send to a specific receiver. So we want the par symbol to be labeled by X2 because that's who is going to receive, who is expected to receive A. And same for X2 is sending this B to 3, and 3 is sending the C to 1. So we need to indicate that in the judgment to be able to then, when we look again in the premise, to be able to have the buffers also labeled by the correct receivers. So each operator of the language is labeled by who is going to receive or who is going to send, and the buffers are also labeled. So that means that, again, all the send operations can happen at the same time, the buffering can happen in parallel, and then the receiving operations can be staged in order to, and again, because there could be conflict in who is going to receive what, we want each operator, also the tensor operator, to be equally labeled by whom the message has been sent. So we want always to indicate the message has to be sent to that person, that process, and I want to receive this message of this type from that process. Because here I took an easy example where A, B, and C were different, but if you imagine that A, B, and C are the same type, then you also want to say, I'm waiting for something of type A from that specific process. So I want all of this information to be recorded in my judgment to be able to then say these types are compatible. Okay, and that's kind of what asynchronous forwarders are. So the forwarders are these objects that that ensure that that these processes are satisfying these syntactic criteria. And so these asynchronous forwarders characterize exactly the types that are multi-compatible in the sense that I introduced at the beginning. That is the semantic notion that was in the literature, in the multi-party session types literature for a long time. And so we have achieved that goal to give a logical characterization of this notion that extends the Curry-Howard correspondence between the session type pi-calculus and linear logic to this wider range of processes. And on top of that, these objects that are forwarders that are computing this compatibility notion, they are also they can also be made to communicate together. So that's an extra step that I don't have time to explain now. Okay, I think I'll stop here. Thank you very much.
So, are there any questions?
Hi, Sonia. Thanks for the presentation. I'm sorry, I have to keep you talking. I didn't really understand how you pick the labels when you're doing the forwarders. Can you go back a couple of slides? When you pick the X1, the X2, how do you know that you're picking correctly?
Yeah, so they are, okay, maybe let's go back here.
Yes, exactly.
Yeah, so the process 1 sends A to process 2. Yeah, exactly. I mean, basically you pick the labels in the way that will enforce what you want to observe, yeah.
Maybe I have a question. So with this result, how can you apply it? So do you have a particular language in mind or set up where you can use it? Or so what is the advantage that you know this precise characterization of multi-party types?
So I don't, because I'm a theorist, but maybe I can ask my co-author. Do you want to say something? You need the microphone.
I guess that this is, you can use this for, I mean, you have a set of processes, and usually this notion of compatibility is, in general, you don't have, if you want an algorithm for checking if these things are compatible, so you could use this as an algorithm. The problem is that what is missing here is that you don't have infinite processes. So and things become harder when you do that. So I believe that the next step here would be to understand actually how to extend this to infinite processes.
So if there are no more questions, so thanks again for the
Thank you.
presentation and the discussion. So, and the next talk should be a remote one. I do not know. So, they are ready to give the talk? Good. So, this is about a relational solver for Java generics type system. And the work is done at St. Petersburg State University, and Peter Lozov will give the talk. So please go ahead.
Hi.
Can you hear me? Okay. Hello, my name is Peter Lozov. Unfortunately, we were unable to attend in person, so there will be a virtual speech. Sorry, I need to switch off my headphones. I hear myself. Yep. Today, we will talk about relational programming and its application to solve Java generic type system inequalities. Well, first of all, we will talk about the motivation behind this problem. As you know, the Java language is one of the popular high-level and object-oriented programming languages. Currently, approaches to verification and automatic testing of Java code are being actively researched. And one of the prominent methods for software testing is symbolic execution. A crucial component of the symbolic execution engine is the type solver. The solver is necessary to check various type constraints. For example, the solver is needed to verify typecasting in code. The solver has to search for all types that satisfy the system of inequalities with free variables, system of type inequalities. In this example, we need to find all types that are subtypes of a list with a specific type parameter, and at the same time, they should be supertypes with the any type parameter. Java generic type system is complex enough that the subtyping relation is undecidable, and direct implementation of the solver is a non-trivial task. At the same time, the verifier of subtyping can be implemented directly according to the Java language specification. This is great news because relational programming will allow the verifier to be used as a solver. And a bit more about Java type system. In the context of this work, we are dealing with the Java generic type system. This is a standard object-oriented language system that includes classes and interfaces with the ability to inherit for classes and for interfaces too. Although classes and interfaces can have generic parameters with various type constraints, like this. Next, let's talk about relational programming. Relational programming is an approach based on the idea of describing programs as relations. It can be considered as a branch of logic programming, but without all non-relational constructs, such as side effects or extra logical features. Also, it uses interleaving search strategy, which is complete. As a result, all solutions are guaranteed to be found. Conventional relational language is minicanonical. Initially, it was embedded domain-specific language for scheme and racket, but then minicanon was ported to many host languages. In context of this research, we use a strongly typed implementation for a camel called acandron. Thanks to the completeness of the search and the absence of non-relational constructs, minicanon allows to express inverse computations. And a lot of complicated programs can be considered as an inversions of simpler programs. For example, the inversion of list sorting is a generator of all permutations for a sorted list. Or the inversion of a type inferencer is a type inhabitation solver. In particular, a solver for some problem is the inversion of a solution verifier for this problem. In practice, this is useful because verifiers is often easier to implement than solver. Let's consider a simple but observable example. there are two versions of piano numbers addition. The first one is functional version in a camel. We can use it for addition only. The second one is relational piano numbers addition. Unlike the functional version, the relation program has an extra argument. This argument corresponds to the result of addition. As we can see, both programs have a similar structure. We have two branches, x is 0 and y is result in the first branch in both cases. And we subtract x and result by 1 and have recursive call in the second branch. And at the same time, the relational version can be used more flexibly. Of course, we can add two numbers, but we can also subtract numbers. This is a simple example of inverse computation. Moreover, we can synthesize all pairs of addition operands whose sum is equal to a given number. We fixed the last argument and we want to find the first and the second argument. As we noted, functional and relational programs are very similar. This is true for many other cases as well. Instead of writing a relational program, we can write a functional one. And then we can convert it using our tool of automatic relational conversion called no-canron. In practice, an automatically converted program is often not efficient enough. That's why we mix handwritten and converted relational code. Well, we have everything we need to describe our approach to solving subtype inequality systems for generic Java types with free variables. We use relational programming techniques like relational conversion and verifier to solver method in our approach. And to boost performance, we also apply some problem-specific optimizations. Our approach consists of two components: direct subtyping relation and closure of this relation. Let's talk about direct subtyping relation first. We implemented direct subtyping relation in a camel according to Java language specification. This implementation can verify that one type is a direct subclass of another type according to given type class table. Then we generated relational verifier using no-canron. This verifier, relational verifier, can search for all substitution for free variables in incomplete types to make them subtype of each other. In particular, a relational verifier can synthesize direct subclasses or direct superclasses of a given type. In other words, it's a solver of direct subtyping. We can use relational verifier as a solver. As I said earlier, the solver will be a part of symbolic execution engine. So we excluded some Java language specification components from the implementation to ensure only instantiable classes to appear in answers. Now let's discuss the transitive closure of the subtyping relation. Closure allows to search for all subclasses or superclasses, not only direct. Closure can be expressed in minicanron directly according to the formal definition of reflexive transitive closure. You can see this definition on the slide. And this relation is easy to express directly in minicanron without no-canron using relational conversion using. After implementation, we found that the performance of the solver was very low. It took seconds to come up with the first solution, even for small class tables. So we implemented some optimizations to improve performance. First of all, we optimized the ineffective parts of the converted code. For instance, nocanron always converts integers to piano numbers because we need to use piano numbers in relational arithmetic operations. However, class and interface identifiers are not used in arithmetic operations, so piano numbers was replaced with integers manually, and it's improve solver's performance. Then we optimized the evaluation of closure based on the groundness analysis of the arguments. We have two closure implementations for finding subtypes and supertypes. And we dynamically select the optimal version based on argument groundness. Finally, we optimized the search in class table. We dynamically construct the search relation depending on its argument's groundness. Let's look at simplified example. This relation is built on a specific class table, very simple in our case. It connects the identifiers of subclasses and superclasses. If both identifiers are fresh variables, we need to do all these unifications, and it's expensive. But if at least one of the identifiers is ground, we can exclude unification from the relations which are guaranteed to fail. For example, if ID of superclass is 4, then we can exclude 4 disjuncts from relation. Of course, this is a non-relational solution because we change relational program during evaluation. However, we only exclude unsuccessful branches. As a result, the set of answers doesn't change, but efficiently increases. We evaluated our solver for real-world class table containing more than 40,000 classes and interfaces, and we use 9 realistic benchmark queries of various shapes. There are 2 single-type inequalities and 7 different systems of inequalities. First, we wanted to evaluate the effectiveness of the developed optimizations. So we tested 4 versions of the solver without optimizations, with optimized closure, with optimized search in the class table, and with both optimizations. Also, our solver is guaranteed to find all the answers, but it may find the same answers several times. To evaluate the number of duplicates, we calculated the total number of answers and the number of unique answers. Finally, to evaluate effectiveness, we measured 4 time metrics. We represented results of evaluation in the form of a bar chart. Here, the groups of 4 bars correspond to different benchmarks. Each bar in the group corresponds to one of 4 versions of solver, left to right, with no optimizations, with optimized closure, with optimized search in class table, and with both optimizations enabled. Below each group are the number of unique answers and the total number of answers. All measurements are presented in a logarithmic scale. We also limited the evaluation time to 5 minutes. And if in a few cases, we received only a part of the answers. In this case, we indicate the time for calculating the first answer only. For example, here, here, and here. Oh, sorry, here, here, here. And In few cases, we did not receive a single answer. The red column is shown in the bar chart in this case. For example, here, here, and here. As you can see from the results, closure optimization, the second column, in each group, improves the result by an order of magnitude, but only for some specific cases. And the class table search optimization always improves the result by an order of magnitude, but the best performance is achieved when using both optimizations together. Although the performance of the solver depends on the order of inequalities in the query. The benchmarks 3 and 4, sorry, 4 and 2 and 3 and 8 and 9 only differ only in this aspect. They differ only by order of inequalities, but we can see different evaluation results. Finally, it can be noted that solving the superclass inequalities delivers a large number of duplicates answers. Benchmarks 5, 6, and 7 contains superclass inequalities only if we can see a lot of duplicates. So we can conclude that optimized version of solver show promising performance results, but the performance depends on the order of inequalities and the presence of duplicates. Well, we developed Java generic type solver using relational conversion and verifier to solver techniques. Then we optimized the solver to improve the performance, and we evaluated the solver performance. This is the approach we are currently working on. Moreover, at the moment, the duplicates problem has already been solved after we wrote our paper. We eliminated duplicate search branches to remove duplicate answers and improve performance. In the future, sorry, I'm again here myself. In the future, we plan to research the problem of ordering inequalities and integrate the solver into our symbolic execution engine. And another interesting problem to generalize our solver for negative type inequalities. A solver for such inequalities is also needed for symbolic execution. That's all. Thank you. I'm ready to answer your question.
Okay, Peter, thank you very much.
Oh, I hear you, but with echo. Maybe I need to switch off my micro. I'm not sure.
We have time for questions,
Yeah.
or are there any questions? So maybe I have a question. So in Minikenran, there is also support for different search strategy. You showed us only how to optimize the subtyping tables. Have you also tried other search strategy, or was it the standard complete, only the standard complete search strategy of Minikenran?
Yeah, thank you for question. Of course, we need to use a complete search strategy because we need to find all answers. But indeed, we have a lot of different complete search strategies.
Yeah.
But when Minicanon was developed, Minicanon authors tested a lot of different strategies, and interleaving search was show the best performance than each other.
Mm-hmm.
So we don't test in other search strategies, and maybe will be interesting research topic for us. Yeah, thank you.
Yeah, yeah. Okay, Robert.
Hello, Peter. Thank you for your interesting talk. I have a question regarding how much do you think it will be scalable up? I think at the beginning you mentioned you have taken a subsystem of the generic type system. Would it be possible to extend it to the entire specification? How is your feeling?
Yeah, thank you for the question. I think this system is scalable because we just repeat semantic of subtype relation. If we have if we want to extend subtype relation, we can just extend functional implementation of this semantic. Then we can translate it, etc. Now our Java type subsystem already contains generic types, generic interfaces, arrays, type variables, intersection types, etc. Yeah. Thank you.
Okay. So I do not see any more questions. So thanks again for your talk. So.
Thank you.
So, and this ends the question, so it's time for the coffee break.
So welcome to the third session of Lobster. It's my pleasure to chair it. And we will first start with a talk by Daniel Rojo Rivas, who's going to talk about a rule-based approach for designing and composing abstract domains.
Okay, can you? Yes, great. Thank you very much. This is a joint work with Jose Morales, Pedro Lopez, and Manuel Menegildo. Analyzing and verifying properties of the programs, it's a crucial part in the software development cycle, and abstract interpretation allows us to do so by constructing sound program analysis tools, which is great, but it gets some cost because due to undecipherability, we always are losing some precision, and eventually we'll need to define new analysis or to combine the others that we already have to prove arbitrary properties. Moreover, the generation of the definition or implementation of new domains, it's costly and it's not easy, and it usually requires a deep knowledge of the framework in which we are defining our new abstract domain, which is an extra problem that we have to face when we try to use abstract interpretation, right? Okay, so for the rest of this talk, we are going to stay in the Horn clauses and logic programming world. So programs are going to have this form, like we have the head, the literals, but we are going to use the prolog syntax instead of the Horn clauses syntax, okay? And a very fast pitch of what abstract interpretation is. Okay, abstract interpretation, it's a technique that allows us to over-approximate the semantics of a program by using an abstract domain. That domain, it's simpler than the concrete domain, that it's the original program, and under some conditions, we have the guarantee of the analysis terminating, which is great, and that we are going to obtain a safe approximation of the concrete semantics of the program being analyzed. In this work, we are focusing in the top-down algorithm that was first used in MA3 and MAs and was mature in Play. This algorithm, I'm going to explain this figure right now. It's separated into two parts. First part is the tree, this T alpha, that it's an abstract domain of the analysis graph, and it captures the path. This path is an infinite object that it's giving us an approximation of the set of maximal entries of the concrete semantics. So, for example, I don't know if you can see this program. It's a simple prolog program that is computing the parity of a list of zeros and ones. So the abstraction of the maximal entries of this program here, it's this graph that we have in the middle. Forget about the nodes. Now we are going to see what it means. But this shape, it's the abstraction of the maximal entries of the concrete semantics of this program here. And the nodes are the data. This is the abstract domain that we are implementing in this example that is given by this very simple lattice. We have a top element, this B representing the bit. It can be 1 or 0, zeta 0 or 1, and bottom that. So this is the framework in which we are working, and we are going to focus in this D alpha that is the abstract domain. Okay. Now, when we want to implement that D sub alpha, that abstract domain, we usually need to define a number of lattice operations that are the usual order. We have the join, you have the mid, we have this nabla, that is the widening operator, which is optional, which is the lattice-related operations, but we also need to implement a number of operations over the abstract substitutions that are at least these 5 operations. You can have more, making it more complex, but you usually have this. I'm going to go pretty fast over them, but we have the abstract projection that, given this abstract substitution, we restrict the lambda to the set of variables Bs. We have this abstract extent that it propagates the success substitution, this lambda S, to the lambda call, the call that it performing the abstract call, that it unifies the literal call A lambda with the head of a clause K defining a predicate A. the proceed that makes a dual operation of the abstract call, and generalize that it's the join, the least upper bound of all the abstract substitution that we have at that point. This framework is, as I said, more focusing the logic programming or constraint home clauses, but it's the same for the imperative world. We only have to change a little bit some concepts that are equivalent. Okay, so now our objectives here are to be able to design a prototype abstract domains and their combination or composition rapidly, and we are going to try to do so by reducing the number of abstract operations that we have to implement, and also trying to make as easy as possible to reuse all the abstract domains that we already have, because it's a work that we already have done, and it will be easy, great not to have to do everything again. So what we propose is a language of writing rules to try to meet these objectives. So this is the syntax of the rules that we are going to use. Let us consider this this number of set of properties L and C1 to CR, and we have this syntax for AND and OR rules. There are the two kind of rules that we are going to use. These L elements, we call them the left side of the rule. They belong to this the first L set. We have all these Ds. Each of them belong to one of these Cs, but not all the C sets need to have a guard. And we can have several Ds for only one of these Cs, okay? As I said, we call them the guards. Then we have this right side of the rule. They also belong to the first set, the L set. And notice we have this label that allows us to know which rule it's been applied over which set of properties. And well, notice the rewriting that we are performing is destructive. So once we have matched the elements in the left side of our store, and if the cards are holding true, the left side is removed, and we replace them by the right part, the right elements. Okay, now I'm going to talk a little bit more about important. From now on, these sets of properties are going to be the lattices of a number of different abstract domains that we are going to work over for combining or even defining. And also, when we talk about the store, we refer to it to the lattice that it's going to be rewriting at that moment, and all the other sets or lattices are going to be what we call the context. Okay. Now consider these sets. We have this store with these less or equal properties. We have this context that it's a polyhedron, a number of constraints, and we have this simple set of free rules. Okay, now the way we are going to proceed, it's very easy for the AND rules. First, we select an applicable rule. This corresponds to this part of our algorithm. After that, the application of the rule will give us an element to remove, in this case, this one, and an element that we have to add, this one. So after that, we do that, and then we update the stores, removing one, adding the other, and we can keep doing the same thing recursively. So the next step, what we do have is applying this rule. So we remove this element and add this new element. Okay, we keep doing it. So now it's this old element which is removed, and we add this here. And we will do it until no more rules can be applied, in which case this function applicable rule will fail, will return false, and then we get rewriting a store. This is the typical way of doing of rewriting a store with rules, and we can do it over a number of stores. In that case, we have to do it, apply a fixed point over the number of stores that can be rewritten given by this set of sets of rules. Okay, now the OR semantics are slightly different because this time we are not rewriting over a single store given a number of rules, but we have two stores, store 1, store 2, and we have these rules. Notice this semicolon that maybe it's a little bit tiny, but what we are going to do this is one of these elements we are going to seek them in one store. The other one we are going to seek for them in the other store. But now, where are we going to rewrite? We need to create a new store over which we are going to rewrite. So let's see. This is a simple algorithm. We are in this situation which we have taken two stores because we can have any number of them. So we apply the rewriting over the pair. We choose an applicable rule. In this case is this one because we have these two elements. They have the same left value, and we know that y is bigger than 3 because of the context. So we enter here, we apply the OR rule, we select a rule, and now we apply the rule and update the store. We create a new store, the rewritten store. We remove the elements and add this right side to the store that we're rewriting. Okay. Now the way of proceed is the same. We remove here, we add here. Okay, we keep doing it recursively as before until no more rules can be applied. But in this case, there are several options. We can not keep applying rules because we have exhausted both stores. We have two empty stores, so I cannot do anything more. Or because I kept with two stores in which no rule can be applied. This is the case. So we check. Okay, they are the same. No, they are different. So we have this problem. Now what we are going to do is we compute the intersection of that two stores because these rules are intended to capture the least upper bound. So when I have two abstractions, if two elements are the same, they are the least upper bound of two elements that are the same element, so I can keep that. So in this case, the intersection is empty. Okay, I get the difference, that it's the union, because the intersection was empty. And now what I need is a function that, given a number of elements of an abstract substitution, returns me the top information of all that elements. In that case, it's just, okay, zeta is at top because I don't know anything about that element. Okay, we do it, then our rewriting store, it's going to be all the elements that I have rewritten, the intersection, that is empty in that case, and the elements that we cannot know anything, so we send to the top of the lattice. Okay, we did that, and then, well, we only have one store left, and we finish the algorithm. Okay, these rules that we have seen can be used to define the fixed point operations that we have seen a couple of slides before, to define them as follows. Now, I forgot to put it, but our lambda, it's going to be a tuple of m lambdas, each of them an abstract substitution. So in the case of the projection, it's simple. I only have to project in each of that substitution. In the case of the extent, what we are going to do is apply the unfixed point over the extension of each of them. Okay, the thing is, as I said before, what we don't want to do is to have to define all these operations. So what we do is the following. For the domains that we already have the operation, the abstract extent, we use it because it exists. If it doesn't exist, then what we are going to do is we need to have a set of rules for that domain that it's capturing that behavior, and we have a number of generalizations of the abstract extent to use in that case. So we would do that and apply the unfixed point, and we get the extent. The same thing happens with the abstract call and the abstract proceed. Okay, and the things are a little bit different in the abstract generalize, because in that case we have to decide what are we doing. If we are only combining domains, or we are using this system to define a new domain. When we are combining, that it's that case at the bottom, the abstract generalize does exist for all the domains, because our domains that are already defined. So we use it, we apply for each of these domains the generalize, and then we compute the unfixed point to make them share all the information, all the possible information. If not, we are going to have this case in which we have a number of domains for who we know the abstract generalize, and others for which we don't. For that we don't know, what we do is to apply the overwriting, and then we also do the fixed point for the result. Okay, now I'm going to do a fast demo, and we are going to consider this property here, inf xa, that tells us that for all the elements in X, that it's a list, A is lower or equal than them. So if we think about how we can implement an abstraction for this property, we could think about, okay, if I know that X is an empty list, I can set this inf to infinite, because I have an empty list, everything holds in an empty space, so okay. If not, if my list is this way, and I know the inf of t, I have two cases. If it's greater or equal, it's lower or equal. So here we have to define this property, what we have is a number of different properties. We have some shape properties. We have some shape properties, but we also have numerical properties, and they are relational, so they are not trivial at all. So here we have that we know that the def_k abstract domain they deal with these shape properties. Polyhedra can handle the numerical properties. So our idea is going to be, okay, let's try to combine this def domain, this polyhedra, and give some extra info to generate a new abstraction. So I'm going to be very fast. So we have this number of rules. I'm going to, okay, now I'm going to this. Okay, so these rules that are a little bit ugly, but for example, here we are getting that if def_k knows that L is an empty list, then I can abstract L to this inf. These three rules, they are abstracting the greater lower bound. So here, for example, if I have two inf elements in my substitution, and I get that X is smaller or equal than Y, I keep the smaller. This one here are the rules related to the list constructor, so help us to know what to do depending the shape that def_k has inferred about our list. And here at the bottom we have these list upper bound related rules that are abstracting things like, okay, if I have in one store this element, in other store this other one, and then I know that the negation of def_k of this one be named the holds, then I keep this. Okay, and what I just run, we can use it to, okay, it doesn't want to work. Okay. I just run this, and this is an analysis that we obtain of using this set of rules over this partition, this partition predicate. This is the normalized version of partition, that what it does is given a list, given a pivot, we get all the elements greater than X go to L2, and the others go to L1, and our set of rules are able to, at entry we don't know anything, so everything is at top, but at exit we get that for all elements in L2, X is lower or equal than than that element, that it's the property that we would like to prove. And okay, we've used this same technique to define this inf. We also did the dual, that it's pretty straightforward once you have one, that is to get the sub. So in this same partition predicate, we get that here, that for all the elements in L1, X is bigger or equal than it. We also use it to get some multiset properties, and we are able to abstract that the addition of the elements in L2 and the elements in L1 are actually all the elements in L, so it's a permutation. And these rule generate domains are also being used to be able to prove shortness properties for a Q-sort algorithm, because we can combine the different information that we're getting from them to get the shortness. Okay, and now I'm going to conclude. Okay, this approach has some, we consider some benefits. One of them is it's pretty simple. The writing systems are very expressive, and it helps us to script and improve abstract domain given some rules in a very declarative way. However, there are some inherent challenges when we are using rewriting. Especially, we have to ensure the convergence, determination, and the correctness, because we are using them to define an abstract domain, and things can be a little bit problematic. And in our future lines of work, we are working in improving the efficiency. Right now, we have a prototype that it's doing a very silly way of applying rule, that checking without a lot of heuristics, and move beyond the prototype and try to do the same things with domains that are already implemented, and be able to compare well the precision gain or loss that we could have. And I think that's all. Thank you very much.
Thank you.
Okay, thank you for the nice talk. And so in this quicksort example, yes, you want to analyze sortedness.
Yes.
And for analyzing sortedness, you also analyze with respect to this inf and sup,
yes,
domains.
Yes.
How do you come up with this intuition that you want these additional domains?
Okay,
so can you automatically infer the new domains, inf and sup, from the goal of proving or analyzing with respect to sortedness?
I don't think so. In that case was because we were playing around the idea of getting more information, combining domains, and we found that, for example, in the example, we could need a number of small properties that all together will give another bigger, and that's why we started doing this. But the idea of automatically detecting which property you concretely need and then generating the domain, it's not. It would be great, obviously, but it's not what we are doing. We know that, okay, I need, in partition, I need this property, so I have this domain, this, and then I mix them using the rules. Okay, thank you very much.
Yeah, hi, thanks. I was just wondering whether the classical ways of combining domains are usually, say, product domain or
yes,
a reduced product domain, which is more can be more precise than the product, which is just the sum of the
yes,
combined precision of the individual domains. Do your constructions correspond in some way to product or reduced product, or are they something else?
Technically, what we have is a number of direct product, and then the rules are acting as the composition predicate that should be reducing it. But
is that the AND rules, or?
Yes, the AND rules.
Okay.
They should be acting as a composition predicate that, in that perfect case, will get the reduced product.
Okay. And the OR rules, are they also?
The OR rules are only for the domains that we don't know, we don't have anything, and we want to generate the least upper bound with them, or the widenings.
Okay.
Thank you very much.
More questions? Maybe I missed it, but it's a naive question. How do you? Where does the rule come? Where do the rules come from?
Oh, the rules are given by the user. The idea is that the user, instead of having to define all the all these operations, can give a set of rules and give adding or removing rules until it gets the abstraction that he desires.
Okay. So I was asking because in your demo, the set of rules look so easy to build.
Yes, well, it's an example that I was been working to see how are the rules, but at the end it was thinking about how do you want to behave the abstraction and keep writing rules, and the idea is to make it as easy as possible. Well, thank you.
Other questions? Okay, so let's thank the speaker again.
I'm just told we have a little bit a connection problem at the moment. Can I suggest we try 3-4 minutes with our video chair to get the connection work? Our speaker is in Tokyo, so it's midnight. I hope he didn't fall asleep. So if I could ask your patience to remain seated 3-4 minutes until we see if we can make it work here. Thank you.
Hello? Bar, can you say something to see if we can hear you? Hello? Can you?
His slides to the session chair. Sorry. Can you ask him to email his slides to the session chair?
Yeah, because he can't screen share.
He cannot screen share.
Okay, so hello, I'm Chantal. I'm the session chair. I will write to you so you can send me your slides.
And we can advance them. Yeah. The volunteer can advance them. Within their. Let me just do it.
maybe I can tell. Can you tell him that he can tell us the slide number, and we will move to the slide number. He can just say.
Okay, so I'm going to move the slides for you. So just tell me to switch to the next slide and I will do it.
See the slide, and so I will talk something.
Okay, so let's start. So we have the pleasure to hear Bar and Nguyen Trong, who's going to talk about design data log templates for synthesizing bidirectional programs from tabular examples. So back at you, and tell me when you want me to switch the slide.
Yeah. Yeah, okay. But unfortunately, I cannot see the slide in any screen. So how to start?
Just tell us the number, and we will move to that slide number. We can see your slides.
For the slide number. Okay. Yes. So my talk is about designing catalog templates for synthesizing bidirectional program from tabular examples. I'm a PhD student in Stuttgart University in Japan, and this is a collaborative work with Professor Kane Chusimba from National Institute of Informatics Japan, and Professor Chen Zhanghu from Peking University, China. In the next slide, slide 2, one of the key concepts in my talk is bidirectional programs. This is a program expressing bidirectional transformation in the consistency between multiple data in different formats. But in addition to a relational database, bidirectional transformation, bidirectional programs also apply in many areas of computing, like programming language, software development. Next slide. Generally, a bidirectional program is a pair of forward program get with the red text and backward program post with the blue text. Get in the right side, you can see the figure of the two programs. Get define a view V over the source S, and put a step an original source S, an updated view V prime, and translate to an updated source S prime. To ensure the consistency, these two programs get and put must satisfy various these properties. Get put and put get. The first property means if you have the VV by the result of getting over the source S, and you use the original V to put back the reflection via the backward program post, you will obtain the original source S. So this means if there is no change in the view side, there should no change in the source side. For the second property, if you provide the original source S, update the view V prime to the backward program post to obtain the updated source S prime, you can recover the updated view V prime by apply the query get over the updated source S prime. In the next slide, slide 4, I show you an example of bachelor program in relational database. Get the forward program is actually a query. Suppose I have a table, a source database with relation S consists of 4 columns A, B, C, and D. I write the query get by dropping the last column D and selecting some tuple with the C value is equal to T. So I obtain the original view V. Suppose in the view side, I have some change from V to V prime with some gray deletion and gold insertion. So this change to the view should reflect back to the change in the source. For example, I have the insertion 0B0T, and this insertion should be reflect to the source with new insertion to the S prime 0B0T and D1. I copy the value of the top insertion tuple in the view side, and for the missing value in the column D, this could be filled with arbitrary thing. For the deletion of 1B, 1T in the updated view, this reflect to another deletion to the updated source. So this is just the example, an example of doing the view update. And the pool program is generally called the view update when we deal with a relational database. In the next slide, slide 5, the thing more complicated if functional dependency introduced in the relation source of view. For example, I have a functional dependency fs that means two dependency a to b and a to d in the original source. So this causing some constraint for data. For example, two tuple in the source with the same value of a should have the same value of b and d. The functional dependency for updated source also sharing the same functional dependency for the original one. And now in the updated view, I have a new insertion. The 1B2T, the second gold rows in the bottom right. And if I do the backward, the view update, and do the similar thing as the previous slide, so I copy some similar value of A, B, and C and fill the missing value of D with D1. So you can see two tuple in the X rows. They are conflict on the dependency A to B, or 1B1 conflict with 1B2. In the next slide, to resolve the conflict, we need some extra effects. This extra effect is the extra change causing by functional dependency. In this slide, in the updated source, I did an extra deletion, an extra insertion. And if you look at the updated source now, all of the data, the golden and the no color rows agree on a functional dependency A to B and A to D. And if you apply the query get over the updated source S prime by dropping the last column and selecting on a tuple with a C value is equal to T, you can recover the updated view V prime, one of the property of where we have this. Next slide, I would like to talk about the challenge. There is the fact that it's difficult to handwrite the query behavior bidirectional program, the well-behaved pair of get and put. We generally familiar with writing a query get, but this is typical to write a view update program put, and it's a thing more difficult if the functional dependency constraint and it has some effect when we write the view updates. We could use some example-based synthesizer to generate a get, a query get, and a view update program put. However, existing synthesizer are almost irrational. They are normally one-way synthesis, and they cannot guarantee the well-behavedness between two independent program get and put. In the next slide, I give an overview of a process and modern example by the top synthesizer, and later you will see process cannot synthesize bidirectional programs. Process is data log synthesizer, and data log is a set of rules. Each rule express a logic formula you can trace from the right to the left, as the right hand side infers the left hand side. Process reduce the synthesis problem to the rule selection problem. Given the I/O example, input/output example, given a fixed set of candidate rules, process try to find a subset of the given candidate rules. In the right-hand side of the slide, you can see the output program consists of 3 rules. That is all the 0 in the candidate rules. Next slide, slide 9, I show you the idea of a process and a challenge to use process. First, we need to have some predefined templates using the template to generate the candidate rules for process. And second, inside the process, there are 2 blocks, a instruction for Z3 and a logic processing block. The logic processing will maintain a synthesis constraint. They ask Z3 for the certification problem, and Z3 model the problem with some value of true and false corresponding to a rule either selected or not selected. And this selection of rule push to the software a data log evaluation. Software evaluates the selection of the rules that evaluates the programs and return the program is consistent with example or not, and include with some feedback if it is not consistent. The challenge, one of the challenge to use process is preparation of the good templates for generating the candidate rules. This challenge make difficult for process to directly synthesize the bidirectional program because we cannot use the common templates for both query and view update. And normally the suspect the templates, the candidate rules for synthesis of get and put have no clear relationship. That's why the well-behavedness property does not achieve. In the next slide, slide 10, I say about some observation and our idea. The first one, when we design the templates, when we define templates, we should somehow we move the well-behavedness inside the template. So if the well-behavedness is embedded in the template, so we have a better constraint between the suspect of synthesis of 2 programs. And second, there is an interesting property is a composition of well-behaved bidirectional programs is well-behaved. This means if we have many smaller bidirectional programs that are already well-behaved and compose them together, we have a bigger program that is also well-behaved. And on relation, we know the forward program get is actually a query, and as a standard, we can decompose query at a a set of atomic query to be small or to be atomic. And in the database community, we know that there are existing studies on view update strategies against each atomic query. And with this strategy, we encode this strategy as the template. All of the where we have this property for bidirectional program will be embedded in the templates. And using this kind of templates is maybe good for synthesis of where we have bidirectional program. Next slide, slide 11. I give you a big picture of our approach. We focus on the synthesis of bidirectional programs from example on relation with functional dependencies. To output the bidirectional program, we require user provide one schema set with a schema of the source S, view V, and some information about functional dependency attached to the source. We don't want to automatically discover the functional dependency from the data. A second thing in the input is one example E with the table of S, V, S prime, and V prime. So from these four type of tables, we can extract the example of the query, example of V update. Our approach consists of three main steps. The first one is that in the left-hand side of the big rectangle, we do the synthesize the query first by adapting processing and using some predefined templates for relational query. So many people do about writing the query and writing the templates for query. After we have the query, we do some process on the query and the given example. By first decomposing query to set up the atomic query, you can see easily decompose to the atomic get 1 to get n, and then we do a forward propagation functional dependency from the source that is already given to all of intermediate relation until we actually view. Look like we forward dependency over the query tree. And also we can forward also the example from the source to the view over the query tree so that we have our own atomic example. The last step is to synthesize a view update program. Now we have the query, we have some information about dependency for several atomic portions. We will design some templates that encodes the minimal effect view update strategy, encodes the constraint and effect of functional dependency, and the web behavior need will be embedded in these templates. And using some templates here, we generate the candidate rules for process, and process return a couple of put 1 to put n, and we can pair with the setup atomic query get 1 to get n to obtain the bidirectional program. Generally, the where we have needs the important properties of bidirectional program is achieved by two things. First is where we have needs of each atomic pair that come from some templates that we already have where we have need inside when we design templates. And second is the where we have needs of a composition of several smaller where we have program. In the slide 12, you can see the three blue highlight portion that corresponding to three core contribution in the paper. First is forward propagate functional dependency. Second is templatized candidates for minimal effect view update strategy, and the last one is design some template encoding the constraint and effect of functional dependency. In some next slide, I will step by step give the example for three core contribution here. Next slide. First is the first contribution forward propagate functional dependency. the goal is to propagate dependency, functional dependency from the source through intermediate or middle relation to the view. Input is a schema of the source that is already provide with functional dependency, and a set of atomic query, atomic rules that is that we can obtain from adapting process and decompose the query. And output is a schema of our own intermediate relation M1, M2, and V. So all the schema in the output should be attached with a functional dependency. The idea is for each atomic query we define how to propagate functional dependency from the right hand side of the rule to the left hand side of the rule for each atomic query rule. And if on relation in the right hand side handle, we propagate dependency to the left hand side. So in this example in the slide, so we start from the source S and propagate dependency to the M1, and in the second rule we propagate from M1 to M2, and the last we propagate from M2 to V. So all of relation in the query tree, we already specify the dependency, functional dependency. In the slide 14, is about the second contribution about templatize the minimal effect VRBS strategies. The goal here is to generate the candidate rules for atomic VRBS. We design the templates that encode the minimal effect VRBS strategy. Minimal effect is a kind of minimal change to the relation. So when we have a Z template, these templates will encode some well-behaved needs of rational program inside. Input for this step is an atomic rule. For example, I have an atomic rule here, and we need an atomic example of the corresponding query and view update. And output is a candidate rules for the atomic view update corresponding with the atomic query in the input. Next slide, I will show you how I design the templates in the slide 15. Given the atomic rule in the input, I will recognize this rule belongs to a sigma rule or selection rule that define a view V in the left hand side from a source S in the right hand side with a list of selection condition. So this is the selection rule. We check the work of Keller and Lasser. They talk about the minimal effect VRBS strategy. There are a lot of strategies. One of them is if we have a new tuple that satisfies the selection condition Fh, and the new tuple is inserted in the view in the right hand side. So the X should appear in the updated source. We make some templates that encode the strategy 1, and you can see in the blue rules in the slide. In the right hand side of the rule, X is a vector appear in the updated view V prime. X is not in the original source, and X satisfies the selection condition because X is not in the original source and following the query in the bottom of the highlight. In the top of the highlight, you can see if X is not in the S, so X is not in the original V, but X is in the updated view V prime. So this is a kind of insertion to the view, and it should be reflected insertion to the source. Here I use some data relation with plus and minus corresponding to keeping deletion, insertion and deletion to the relation. And later, if you would like to compute the S prime, the updated source, we could use the original source minus some deletion and plus with some insertion. With this template, we can generate the candidate rules by some substitution. S is in the position of M1, V is M2, and vector H, the attribute vector should be replaced by V0, V1, and V2. This is just a simple case, but in the complex case, you can generate the attribute vector H by some function of H with the other thing. More technical thing you can find in the paper. In the next slide, 16, this is the first thing in the first contribution for templatize the constraint of dependency. The goal is design some templates that encode the constraint of dependency. We do not want to own a tuple in the view side could be referred to the source. Some tuple should satisfy some constraint, must be possible to reflect, and the other invalid tuple should be rejected. Input is the schema with a functional dependency. For example, I have M1 with dependency from A to B. And output is a candidate rule expressing a constraint of dependencies. So this rule means if we have a two tuple in M1 with the same value of A position, but different value of B position, for the other position we do not care. So a special relation FR will hold the special reject value. The idea is we use negative constraint to express the integrity constraint. That is based on the VII. Normally people use the bottom choose value of false to express the negative constraint, but the proceed does not work well with null relation like bottom, some relation with empty attribute, empty variables. So we replace bottom by a special relation with that holding one attribute. It's just tricky. In the next slide, 17, besides the constraint of dependency, there are also some effect of dependencies. If we have some insertion from M1, for example, 1B to T must inserted to M1 by V update, but this conflict with the tuple in the original. So there's two strategies. First is we delete the conflict tuple, and second is we revise the conflict tuple by the must inserted. So for the effect, we also need to design some templates to encode these effects to strengthen the search space. And input is a schema, atomic query, and example output is a candidate rules expressing effect of functional dependency. And depend on the example falls into what kind of strategy, deletion or revision. We generate a different class, different set of rules. So just note here, if we have a more functional dependency, so we should have automatically generate more candidate rules here. We implement a prototype named SimBP for our approach with 8,000 line of Python. And we would like to answer a question that can our system synthesize bidirectional programs from example with and without functional dependency. We adapt from VII 2032 benchmark. In the slide in page 20, you can see this shows the metric of the benchmark. There's at most 4 relation, at most 30 attribute, some 16 benchmark with functional dependency, 16 without functional dependency, and some dependency is actually is a primary key. For example, the first one, and some is not a primary key. For example, in the 16, the benchmark 16. And the example size is considered as a reasonable size because we know protein have some trouble with the big size example. In slide 21, we show the preliminary result. And to answer the question about the capacity of our system, people like to say that our system can automatically synthesize 31 out of 32 benchmark. There are only one failure in the last benchmark because the query considered aggregation is not supported to there's not so much information about the VRS strategy for aggregation, and we cannot make some templates for that one. And for the other benchmark in this slide, you can see our system can handle a variety combination of query, just from one single query to 10 combination of 10 queries. Okay, in the last slide, so in this talk, I give you an overview of our approach for synthesizing bidirectional program from example with functional dependency. There are three core contributions. Forward propagate dependency from the source to the view. Second is making some templates for minimal effect VRS strategy. And the last one is making some templates for encoding the constraint and effect of dependencies. The grab-behavior bidirectional program is guaranteed by the grab-behavior needs of templates and the grab-behavior needs of the composition. In the preliminary experiment, our system is powerful enough to automatically synthesize many interesting bidirectional programs. There are three future work. First is to study the VRS strategy against aggregation. That is one of the failure in our experiment. Second is to templatize the more type of dependency, not only functional dependency, but also inclusion, exclusion, or domain constraint. And the last one is to seriously estimate the closeness of the output program with the user intended program. So far, our program is composed of several things so it's a little bit complex and a big. Later, maybe we still need to optimize the output program and have some score function to estimate the closeness. Yes, so that's all for my talk. Thank you for your attention.
First, I apologize for some slides not displaying well. Are there any questions in the room or online? So I do have a question.
Yeah,
on
please.
slide 9, you mentioned provenance. Can you say
yes.
if in your contributions if you are using provenance information to? Yes. So here you on slide 9 you said you get feedback with provenance from Soufflé. Do you use this feedback in your work?
No, I just focus on the design templates here, which and we use this big system.
Okay, so it's used in other parts.
Yeah.
Okay. Other questions? So thank you again and for giving the talk in these conditions.
Thank you very much.
And I think the session continues with the Best Paper Award.
Thank you very much. I would like to thank everyone for your patience with all the technical difficulties, and let's give our video chairs and volunteers a big hand, and also our speaker. And also let's give Chantal a hand for an extraordinary cheering activity. Thank you very much. So we come to the last highlight of today. It's the Best Paper Awards, and they are kindly sponsored by Springer, who is also producing the proceedings. And I would like to use the chance to thank Springer for an excellent collaboration in publishing the proceedings in time for our meeting. In response to our call for papers for Lobstra, we received 29 submissions. out of these 29 submissions, our program committee, sometimes under extensive discussions of the paper, selected 12 presentations. And then out of these 12 presentations, the program committee voted for 2 best papers, one in the category of short papers and one in the category of regular submissions. And the winner is, of the short papers, it's the towards a certified proof checker for deep learning. If please. So, here is your award.
Oh, thanks for that.
Thank you. And in the category of full regular papers, the PC voted for the constraint horn clause satisfiability that we'll see tomorrow. And so congratulations also to that author team. That's, yeah, maybe you come forward. The authors. So you also have a certain yeah, congratulations again to our 2 best paper award winners. And again, yeah, we'll see. We have seen one today, and tomorrow we see the second paper. Yeah, we are coming to an end, and I would like to thank the speakers, all speakers of today, also our invited speaker, Maribel, who is here, for the excellent presentations and talks. Let's give them also a hand. And tomorrow we continue with 3 more sessions, and the first session in the morning will be opened by our keynote speaker, Manuel Hermenegildo, on the fly verification using incremental abstract interpretation. So that will be at 9 o'clock tomorrow, and I'm looking forward to see everyone tomorrow fresh in the morning in the same room as today. Thank you very much.